So first, I welcome our today's guest. It is my great honor to introduce our today's distinguished resource person, Dr. Jayesh Barve sir, who is currently
Yes.
serving as a principal controls and optimization at GE Global Research Center, Bangalore. Dr. Barve has remarkable career of over 30 years, combining more than 16 years of industrial R&D experience with 14 years in academia. He has been associated with the Controls and Optimization Group at GE Global Research Center for more than 14 years and earlier contributed to the Technology R&D Group at Tata Consultancy Services, Pune. A prolific researcher and innovator, Dr. Barve has filed more than 20 global patents with a few more in pipeline and has authored over 50 research papers in prestigious international journals and conferences. In addition, he has contributed over 25 industrial technical reports at TCS and GE. What makes his contribution truly impactful is that his research has translated into practice, resulting in over 15 industrial products developed for GE Industries. With his unique blend of academic excellence, industrial innovation, and research leadership, Dr. Jayesh Barve continues to inspire and advance the fields of control, optimization, and applied research. We are privileged to have him with us today, and I warmly welcome Dr. Barve to our ATAL FDP. We welcome you, sir.
Thank you. My
Yes, sir.
pleasure.
Thank you.
Welcome, sir.
Thank you, ma'am.
Okay, over to you, sir.
Okay. Yeah, I was trying. I don't have. I think you have to share screen. Give me rights to. Now I have. Okay. Can you see my screen?
Yes,
Yes,
sir. Yes. Completely. Yes.
Okay.
yes.
What I would do is, I think, let me switch off my video. Just for the network speed, because it's raining in this area.
Yeah,
This
yes, sir.
network is a bit weak.
Okay,
And switch off my video for the bandwidth.
yeah.
Okay, so good evening, namaste, and happy Ganesh Chaturthi to everyone.
Same to you, sir.
Thanks
Happy
for
Ganesh
the
Chaturthi, sir.
invitation and opportunity. Thank you. So, thanks to Professor Chetan, ma'am, as well as team, and Professor Ajay Deshmukh for giving this opportunity to be able to share some of my experiences for the benefit of faculty and researchers participating in this particular FDP. So, as we know, the theme of the FDP is Next Gen Manufacturing, Embracing Industry 4.0.
Yes.
And basically focusing on manufacturing and industry 4.0. So the topic which I am trying to talk about is sharing some of some of the academic work as well as some experiences in industrial automation and robotics, evolution and emerging trends. So I will not be talking about specific work, but just in general, trying to share some of the interesting trends in this particular area. Yeah. This is the abstract. Okay, this is, I'll skip this slide. You already introduced me. This is just a summary of my introduction overall work. Yeah, so before I think we start on the industrial automation robotics area, I would like to give a brief overview of where I belong to. Right? So I'm
Okay.
part of G Varnova. So if you remember, G is a company started by Thomas Alva Edison in 1892, General Electric. So one of the leading global technology company, which has been working in different areas. Started with appliances, right? Light bulb, Thomas Alva Edison. To appliances, lighting appliances, then oil and gas, aircraft engines, turbo machines, basically. Aircraft engine, gas turbines, steam turbines, healthcare areas, digital X-ray, MRI, CT scanner, and so on. So multiple different domains, including IC engine, heavy-duty compressors for the oil and gas pipelines. So these are the different areas where GE has been working across, including transportation locomotives, right? So high-duty diesel engine locomotives and so on. A year back, or more than a year back, GE was split into three businesses. So one is GE Healthcare, which got separated more than a year back, or rather 2 years back, and GE Aerospace, which is mainly focused around aircraft engine and some of the technologies around that. And third portion, which is all power or energy business, that is separated as a GE Vernova. So, which is April 2024, we actually separated, including in this separation in the stock market. So we are a separate company in the share market. So GE, all three companies carry GE logo and GE name. So GE Healthcare, GE Aerospace, and GE Vernova. So Vernova is again, we call it as a mini GE again, because it's again having a multiple verticals. So Vernova, if you see, it's overall into three different business verticals. Conventional power, which has been, GE has been into it. So coal power, gas power, basically fossil power generation. Right? So we supply, we are not power producer like Adani or Tata Power. We supply equipments. We manufacture, develop technologies, manufacture equipments like coal power boiler or HRG, heat recovery steam generators, steam turbine engines, steam turbines, generator for the coal power plants, right? And some flue gas treatment systems and so on. So we are into those areas. So that is a traditional conventional power business. But now, because our motto, if you see, we are playing into energy transition for the world. So decarbonize and electrify the world. That's our main statement, right? For GE Vernova. So we are focused around that because with so many decades, industry, like basically humankind, we kept on working on the power which is essential for any nation or geography and humanities to grow for the betterment of life and livelihood and for betterment of industry. But doing that, we actually decarbonize, we basically generate a lot of CO2 and global warming effects. And because of that, we have started impacting the Mother Earth. And that's where few decades people have started thinking about. We should do something, otherwise what the future we will give it to our next generation and maybe generations after that. So we should keep the world which is livable. And for doing that, focus has shifted last couple of decades. And we have been in forefront of that, which is an energy transition in such a way that you generate electricity. We develop equipment and supply equipments which can help generate electricity for the world, but at the same time also help the Mother Earth without impacting it much. So in the conventional power, we are mainly focused around decarbonization. So in conventional power, we have gas power. Of course, nuclear and hydro are anyway non-emitting, so they are the clean energy. But gas power and steam are the major. In nuclear also steam turbines are there, but emission is not there. So gas power and coal power, those are the major businesses which are having using the fossil fuel. So we are working on the decarbonization technologies. And for decarbonization, what is basically focused on is you have the flue gases. Those flue gases, we actually do carbon capture, right? So the technologies to capture carbon from the flue gases coming out of the coal power plant or say gas power plant. So we are mainly focused around the gas power plant output. So there are technologies which are being used, say in IC engine, people would are aware. We have an exhaust gas recirculation, right? EGR, which is a technology used in the IC engine, diesel engine, to reduce the emission. So automotive, these things came up earlier. for the diesel engines and all. But same technology, but if you see the scale, diesel engines and all, they are in the say locomotive diesel engine will be say 3-4 megawatt capacity. But we are talking about power plants which are generating 500 megawatt, 600 megawatt, 700 megawatt in that scale, right? So how to do exhaust gas recirculation in those areas, in this particular scale? How to do carbon capture, CO2 absorption, NOx absorption? Anyway, we have technologies, sulfur dioxide absorption. There are FGD technologies are there, but CO2 absorption, because CO2 is a main byproduct of main product of the combustion, right? C plus O2 gives you CO2. So once you have proper, efficient, and good complete combustion, you have to have CO2, which is output of any fossil fuel combustion. So CO2 you cannot avoid, but whereas NOx and SOx are in few percentage point, right? in ppm level. But CO2 is a major outcome of any coal and gas consumption, combustion. So how to decarbonize, how to capture carbon dioxide from the flue gases? So you minimize the CO2 which is going into environment. And what is done is this CO2, once it is captured, either it's absorbed into some material technologies, or it can be compressed and sent it to undersea, or to the mines, or undersea oil and gas fields, which are emptied, right? So once those gas is extracted or oil is extracted, those mines are there where you can pump those. So these are the technologies where we have started looking into. So that's where we call it decarbonize the world. So because power generation you cannot stop. It is essential for any humankind or any nation, any geography, for the growth and development, to make the living better with all the facilities, to make the industrial productization better with electrification. So electricity you cannot stop. So generation will not stop. Generation will not reduce. Many unelectrified countries or world, generation will keep on increasing. Many developed world, generation again will keep on increasing, because lots of technologies are moving towards electrical. Many technologies which are working on, say, engine. Take a case of automotive itself, right? So engine technologies, IC engines, people have started moving from IC engine to now electrical vehicle, right? So EV. So electricity you cannot stop. Electricity demand is will keep on growing. So power generation has to happen. You can stop it, but how to generate power so as it does not affect the Mother Earth, it does not create global warming, and that's where this technology R&D comes into play. So decarbonize the world. That's the main focus in conventional power area. In addition, GE Vernova also have renewables in its kitting. So in addition to conventional power generation sources, we also develop technology and supply technologies for wind, onshore wind and offshore wind. So wind turbine, we are one of the leading, maybe top 3 players globally. So we manufacture wind turbines right from, say, 1.5, 1.6 megawatt scale up to single turbine can generate 14-15 megawatt power. So this is the scale of wind turbines which we are into, including offshore. So very large power wind turbines are for the offshore. So they are in the sea. So they are commissioned, installed in the sea. Onshore are on the land, right, near sea or in the normal land area, in the hilly terrain or near the seashores, and so on. So wind turbine is again a very complex technology, and we are into it. We also manufacture, because wind turbine requires a blade, which is again a complex flexible structure. Light glass fiber material are used, including some of the components may be carbon fiber. And to give you an example, these blades can be very long. If many of you might have seen the blades, either on the road or in the wind turbine in nearby your area, in Chitradurga or say Kanyakumari, in Gujarat border, seashore areas. So single blade turbines can be, say, turbine tower can be almost 130, 140, 150 meter tall, and single blade length can be, earlier it used to be few tens of meter, but nowadays it's a 70, 80 meters, and for offshore it goes all the way up to 110 meter. And then such a large complex turbine, which is rotating machine on a tower which is actually unstable structure, which is a oscillating structure, right? So it's a tall tower, maybe 150 meter high, small tower, which is having a rotating blade, which is a heavy mass, maybe 50 ton of mass rotating, 50, 60 ton of mass rotating there. So it's a very complex mega machine structure, stability of the structure, stability of operations, and it should be fit and forget. So wind turbines have a life of 20 years, 25 years, and so on. So how to ensure this works fine. So it's a very complex technology. So, but then this is going to accelerate, right? In addition, we also supply, we also have solar battery hybrid systems and so on. So in renewable, we are basically focused on how to accelerate the
Hello? Hello? Hello, sir. Hello? Hello? I think there is a connectivity issue. Just wait, all the participants.
hello.
Ah, yes, sir.
Okay.
Okay.
So I don't know where I was talking about still our technology GE businesses.
Yes, yes.
Okay.
Share the
Basically, what I wanted
presentation.
to convey is rather than repeating, I'll just say we are into all the conventional power and renewable areas, right from gas, coal power, nuclear, steam, hydro, onshore, offshore wind, as well as hybrids, solar and storage solutions for the megawatt scale storage, battery storage solutions. For the utility scale, right? Not EV scale, which is a few hundred kilowatt or a few tens of kilowatt. We are playing in the from megawatt scale storage. In addition, we are into grid solution, power conversion and grid solutions. Power conversion is focused on how to electrify many industrial sectors, like steel plant or paper mills, right? So they have lots of electrification happening. So large scale drives, so power converters for them, or many large equipments, blast furnace, power electronics for those furnaces and so on. So that's a power conversion business works into industrial load side application of power. And we are into grid, so transmission and distribution grid to connect power generation resources towards the load, right? So through substations, we have substation technologies, grid automation business, which provides those. And we have transmission grid management, grid operations, grid optimization solutions, grid OS, and so on. So we are into all these areas. So basically, GE works into this, so decarbonize and electrify the world to make the world better by providing solutions for to meet the world's energy transition into new era now. So this is about GE. Now, in addition to this, all businesses, we also have some vertical. We call it as a rather than vertical accelerator or horizontal, which is energy financial or energy consulting services, and ARC, so Advanced Research Center. This we work collectively with all the businesses. So our projects can be across multiple businesses. So businesses have their own technology engineering team, plus production team, manufacturing team, supply team, sales team, and so on. I'm part of Advanced Research Center. So we basically look into next generation technology development, supporting all these businesses. So we do early TRL, low technology readiness level technologies. We explore those technologies, build, explore them, develop some things, build proof of concept prototypes or technologies, some solutions. And then once solutions are viable, business takes it forward. So we transition them to business, work with business to complete the productization based on the need. We support them hand to end. And once productization is done, then business takes it over from there to do the normal regular engineering of those technologies. And then we start looking into different projects, different areas to do innovation and R&D. So this is what Advanced Research Center
Sir,
does.
please share your presentation.
Yeah, I'll share some of this. Yeah.
Yeah.
And this is anyway open, so I already put in the links here, so you can also look into those. Now, in Advanced Research Center, just to give you, because this is also a research, mainly participants are research and academia. So also just for information, so Advanced Research Center, we are about 250 plus researchers globally at two centers. So one center is in Albany, New York, which is having about say 150 to 180 researcher, and about 80 to 90 researchers are in Bangalore. So we are two research centers collectively, and these are all mainly 60 to 70% of researchers are with PhD, postdoc, with long experience like me, 20, 30 years and so on, and some freshers. And remaining 40% are usually 35 to 40% are mainly the masters, MTech scholars. And groups are, we have experts in the different areas. We call it the different labs or different technology organization. So like we have researchers, teams, groups, aerodynamics and thermosciences, AI, robotics and software. We have control and optimization. I'm part of the digital control and optimization group. Electrical power systems, they work on mainly power electronics.
Hello,
Embedded
sir.
systems, cybersecurity group,
Hello,
material
sir.
chemistry and physics. Because see, all technologies which I mentioned, right, GE businesses does, this is actually all interdisciplinary, multidisciplinary work. It cannot be one particular domain. So we have actually R&D groups consisting of all these different expertise, right from materials, coatings required for the gas turbine, for high temperature turbo machine, right, gas combustion, and so on. Mechanical system design, to electrical power converter systems design, power systems design, to AI robotics for the asset management, and some of the even Gen AI work we have been looking into. And of course, aerodynamic and thermoscience is important. And controls and optimization across all these applications is what I'm part of. And we are almost about 100 people working in this area. About 80 to 100 people. About 50, 60 people are in US, and about 20 people working in control and optimization in Bangalore.
Hello, sir.
Yeah.
Hello, sir. You not shared your presentation. Kindly share it now.
Oh, okay. Oh, I thought you were talking about will I be sharing my presentation?
No. For session only.
Sorry about this.
Okay.
I think in between, I think there was must have been a power, some signal drop.
Yes, correct.
Okay, can you see my presentation now?
Yeah. Yes, sir. Yes, correct.
Okay, so what I was showing is this about the GE. I just wanted to give a quick overview of GE, what it does, GE Vernova, and these are the different R&D groups, right, which we work on. And I'm part of controls and optimization across this. Okay, so with this brief introduction of my company, just for the knowledge and awareness, I will come to the topic. So I divide my overall agenda into three different areas. Automation robotics, will briefly talk about history of it and some introduction. It's more academic interest for this part. Then quickly I will go through evolution of hierarchy and building blocks of industrial automation. So how those building blocks have evolved over last 100 years and so on. Initial history I will cover right from very old time, just for academic interest, because I know this is also an academic population in the audience. And then quickly we'll talk about industrial automation robotics emerging trends. Okay. So this presentation. Okay. So if we talk about automation and robotics, so it's a very ancient era. Also, it has been existing if we basically observe and look into some of the ancient literature, right, or scriptures. So, but before we talk about that, just a basic observation: why automation and robotics has been thought through or has been invented by human, because typically human has a tendency. We don't like to do routine, cumbersome, or unpleasant tasks, right? Typically, if you have to do something very repetitively, or automatically in the back of your mind, you will think, okay, should I do something to get rid of that? Can someone else or some machine can do it for me? That's a normal tendency of any human being, any intellectual, anyone from that perspective. But at the same time, whoever has to do that job. So earlier it used to happen that in caveman's era, people used to do a lot of work by their own. Then they started finding human labor or slaves who can do their job. So more intellectual people or more thoughtful people, they started making others as a slave. But then, which is slightly inhuman, which is not human that way. But then the same intellect people also think of, okay, slaves' life, how can I make their job easy, right? So they don't want to do the work themselves. They engage slaves or other humans or animals to do that job. But they also think, it's a normal tendency. We also think that, okay, how can I do something so it will make a job of animal or other human slaves who are doing my job, how their job can become easy. So as an example, animal and human pull carts, people invented a wheel, right? So tire and wheel, metal wheel or wooden wheel first, and then wooden wheel, metal wheel, then wheel using the tire, right? Tire tubes and so on to make their job easy. And then also started looking into mechanization. So even how to exclude human and animals from this job or repetitive task, and then started coming up with a vehicle, right? First steam engine based vehicle, IC engine based vehicle. Even before that, cycles, right? Pedal cycles, cycle pedals, and so on, to make the job easy. So this is typically always the case. And of course, other thing is good and evil always coexisted right from the ancient era to up to modern era. And coexistence of this, so good people always have to find some means to handle how the notorious things caused by the evil people, right? So even today, if you talk about, so earlier era, the evil used to say rishis, right? In our case, in Indian scriptures, Rishi Munis, they could not do their knowledge gathering or yagyas because asuras used to harass them, right? So to handle them, then they had people, they had engaged warriors, right? And gods like Rama, Krishna. They fought them and they got rid of them. Using some of the, and for doing that war, they had to invent some of the aspects, some of the tools or mechanisms. Simplest is a bow and arrow, right? And then subsequently it came up to even then swords, and then topes and so on, right? So those are the things. And today's era also, you have evil people who are doing cybersecurity wars, right? So they do hacking, they affect the digital technologies, and then they try to do harm to any nation or any industry and so on, or to any human. So how you need to handle this? So all these things coexist and start happening right from the ancient era. So if we take the case of all these aspects, if you see, so where automation and robotics have started coming into right from the ancient era. So though the words may not have been used, but the thought process has been there. So if you take a case of Rig Veda, 1500 before Christ, Sambarasura is mentioned, the devil, which was created, who created Dhamma, Vyala, and Kata. So three human-like slave, they call it. In the scripture, it is mentioned as a three human-like slave, which were lifeless, who did not have any senses, no emotions. You can say now today, you can see this, what is it? This is like a robot, right? It's a mechanical man or human or animal who does not have, who has a very high strength, but they are lifeless and they don't have sense or no emotions. So they can be very hard to defeat in the war. So this was the mention in Rig Veda. Yoga Vasishtha talks about Maya, robots and artificial intelligence. Can you, like today we call about AI, right? Artificial intelligence. Maya is similar to that, which has been mentioned in Yoga Vasishtha, which is maybe about 1,000 to 500 before Christ. Mentioned in the Vasishtha Rama discourse. So during the discourse, this has been mentioned. Maya, I can term it as a AI, right, of the today's world. Ramayana also, it's about say 700 to 500 before Christ. You have mantra powered bows and arrows. Is it a software? Can we see it as a software? Of course, right? So you would have seen the Ramayana serial or Mahabharata serial, right, on the TV, or even you have read those books. So Ram or Lakshman and all the warriors, and God, they used to have the same bow arrow, but the arrow can be same arrows can be, they chant some shloka or mantra, and the arrow becomes Agniban, or arrow becomes Vayuban, and so on, right? To harm, or even from same arrow you can have multiple arrows. So it's a multiplication of like scattered bomb kind of thing. So those concepts were existent, right? And mantra is like a software, right? You're changing by just programming something. Pushpak Viman has been, everybody is aware. Pushpak Viman is a flying chariot for a faster journey in those days. So this is what, if you see the historically, concepts of automation and robotics, they are existent in a different ways, right? If you come little later, say in Egypt, so in ancient India's scripture, it is already mentioned, right? We are one of the oldest civilization, and these things exist. If you take later civilization, Egypt, there is a mention of float regulator for a water clock, right? So it's a Sibius water clock machine. It's like some automata machine, mechanical auto, fully mechanical. Similarly, there is a mention of in 10 to 50 after Christ, right? In Greece, there was a temple. Basically, it's a church door or temple. They call it temple church door, which is a huge door, and that door can be opened by Aaron's automata. So you put a wood fire, and with this wood fire, this particular whole mechanism with a chain pulley and some pressure generation, because once you put wood fire, water will boil, it will generate some pressure, and that because of this pressure, there will be some motion, right, with the vapor, and that will rotate some of these chain pulley mechanisms, and because of that, the door will be open. So to open the door before the church time, they will just put a fire. So it's little time before, and then church door will be open, because these are the huge door, right? If you see ancient churches or even ancient temple, there are huge doors, or forts, they will have huge doors. Similarly, there is a Ilopile. Again, it's a mention in the older literature. Some of the systematic engineering of the modern world, if you see, 1750 AD in UK, James Watt invented a steam turbine. Right, the steam turbine has this flyball governor. Steam engine has a flyball governor, which is actually a very nice modern automatic feedback-based control system or automation system. Where, hello, I see some noise in the background. Are you able to hear me?
Sir, I will go.
Hello. Hello, am I audible?
Yes, sir, you are audible. You are audible.
Okay. So there is some noise in the background, so I thought. So the flyball governor, it's a very interesting mechanism, right? So as your speed of the engine increases, the flyball, because of centripetal force balance, it will expand, and because of that, this lever will pull up, and there's a valve connected to that. So as based on the speed control, this will be based on the pressure, spring pressure applied to this flyball governor mechanism, right? And based on that, at a particular speed, this is balanced properly, and right amount of flow of fuel to this engine will be regulated. This is a modern day. This is the first example of a good design or engineered, human engineered good automation system. After that, if you see 1805 AD, there's another example which is more close to a robotic kind of example. The French mechanician Henry made a draftsman writer who could actually write and play music. Right? So this is the system for that. So it's again a completely mechanically programmed. So you will have mechanical rotors, and on this rotor, different like if you know printing press, right? So printing press will have olden days printing press had those all the letters marked engraved on the mechanical components, right? So small components pieces. Similarly, here it will have a rotary rotor disc, which will have different dots and lines marked up or engraved. And as this will, you know, old days clock, you have a spring loaded clock, right? So you give a key, so spring will be tightened, and 24 hours that spring will slowly release, and it's so well designed, so it will be giving you a time, mention of time, right? 24 hours. Similarly, those discs with the spring loaded, then those discs will have some engrave marking, and as it is rotating, you will see that some pickup points on those discs will be able to create some kind of music. So it's a programmed music, pre-programmed written music, or you can even write a text based on that, right? So coming to later part now, so in the 20th century, so 1921, that is when the first time they use, so far nobody used the term robot, though they were mentioned of those kind of devices or machines. First time the robot word was used in 1921 in a robota, robot as a word robota, which was part of the play. RUR was a play name, right? The RUR is a play. It's a Czech play in 1921 by Karel Kapell. And in this play, it's Rosem's Universal Robots. That's the play title. RUR is for that. So that's where the first time robota word was used. And in this play, there are multiple artists, multiple, you can say, actors, right? Actors in the play. And they were having like this, Sola was a robotess, Marius was a robot, Radius is a robot, Damon was another like able robot, Helena is a robotess, and Primus is a robot. This play is working around this robot, and it was basically talking about the word robot first. So this is slowly where this terminology has started coming in. So with this old ancient history, I will come to now the basic introduction of automation. Now, of course, all of us know automation or automatic control is use of various control system for operating some of the equipment. Right. So systems and machinery, it can be systems which you want to operate. So automation includes sensing and instrumentation and controls, which enables outcome of make is outcome of digital transformation. And it uses various control systems, sensing systems, actuators, and so on, different components to operate certain equipment or system or machine to make the job better. And these machines or systems can be from any domain. It can be mechanical system, like in a manufacturing plant for the automotive or discrete machine manufacturer. It can be process industry where you are manufacturing some chemicals or petrochemicals, or you may have refinery. It can be power plant, power generation you do, or power transmission, or it's an automotive, which is a mobile machine, or it can be even a small machine in the home appliances, right? So these machines can be from any domain. It can be ships or aircrafts or automotives or transport systems, right? Rail, metros, and so on. It can also be switching and telephone networks, right? So any systems, you add some of the sensing and some intellect or some algorithm, which can be very simplistic like on-off control, or it can be very complex with model predictive control or advanced AI-based controls and so on, or it can be more simpler PID controllers or very simplest on-off control and so on, or time-based controls, right? So these are the different mechanisms. So whatever this collection of these things is called automatic control, the purpose of which is to do minimal or reduce human intervention, right? That's the intention. Because that's always automation purpose, but when automation is invented by human, mainly to help him to avoid repetitive tasks, right? So earlier, boiler was operated manually. Person has to go change the set points. Now those set points are, instead of going near the boiler, they are done from the control room, right? Similarly, automotive, those who have seen automotive vehicles, say cars and scooters in 60s and 70s and 80s, and now if you see today, there are lots of digital technology, sensing and automation has come, right? As lots of electronics has come, and this is all happening. And overall purpose is to do all this job by the system with minimal or reduced human intervention, right? It's mainly to make humans' life easy and get rid of repetitive tasks. Right? So that is the purpose of any automation or automatic system. System is, I'll just skip for the benefit of time. This is just simply a collection of components. We're having interaction between them. Like there's a process control example, same way you can have automotive, where you have feed pipe, you have a tank, you have stirrer, all these mechanical components, some cooling water line, jackets, or tubings, and then valve. You want water has to be from top. Say output water line should be from bottom, so feed can product can go out. You should have some jacketed heating for jacketed cooling or heating. You should have that particularly designed. So this is actually collection of different component systems or subsystems having some kind of interaction. There should be heat transfer, right? So between this jacket and the tank, liquid in the tank or material in the tank, to meet certain objectives. So here the objective is to cool this particular contents or material inside this tank. So to meet this objective, you have this kind of components having some kind of inputs, feed and cooling water flow or inputs. Output is like product which is going out at a particular temperature, and cooling water which is after the use of throwing away cool to this material to cool it, slightly hot cooling water will come out. Right? It can be recycled or it can be thrown out. It's a different part. And the primary objective of any of such system can be either a quality of this product is to be maintained. To maintain the quality, you need to keep it at certain temperature, and that may be a primary purpose. Secondary purpose here can be like a temperature control. Right? So this is a system, but system alone is not sufficient because you don't want system to only meet your purpose, right? So meet your objective. The objective has to be met within particular performance specification. As an example, product is to be, this primary objective is to maintain quality. To maintain quality within, say, ppm level, say plus minus 5, I need to keep temperature within plus minus 5 degree or plus minus 2 degree. So I will have certain specification. If there is any deviation in the feed water temperature, how quickly this temperature has to be controlled, because if feed water temperature changes or cooling water temperature changes, my product temperature will change momentarily. But then it has to be how much I can allow it to deviate. So you will have in secondary parameters also, you will have some specification. We call it a performance specification. So when system needs to meet objective within the performance specification, systems alone is not sufficient. You need to put additional components in the system which can verify the performance specs, and any action, corrective actions to be done, or any reactive action or proactive action to be done can be taken care of by the additional components. And which are the additional components? These are typically sensors, because I need to measure the temperature. So in original system, I add a temperature sensor. Temperature data has to be transferred to my controller, which is a decision-making element, right? Who has electronics, or it can be pneumatic, or it can be hydraulic system, whatever, or computer system. This data will go, it will have some algorithm which is built or programmed, or it can be programmed through pneumatic way, it can be programmed through electronics way, it can be programmed through, say, software way, right? Depending upon those evolution has happened over maybe tens of decades. So today, most of the systems we use programming. The software takes care of all the decision making or intellectual. So data goes, some computer, some crunching is of the numbers is done, and then some action is to be taken. Action is transferred by the decision making block, and it goes to the actuator. Actuator will decide to maintain temperature what I should do in terms of whether I should increase or decrease the cooling water flow so that my temperature can be maintained within the performance specs. So all these three are the key elements in addition to my basic system. And those three elements, major key elements are sensor, controller, we call it controller or decision making element, and actuator. And in between all these three components, you have a signal to be transferred from one, say, sensor to decision making element or controller, and from controller to my actuator. So you need some transmission mechanism. The transmission can be analog, can be pneumatic, analog, can be hydraulic analog, it can be electrical analog signal, or it can be even the protocols, or we use TCP/IP with all these protocols. It's a digital communication. So these are the communication technologies which are part of the additional components. All together becomes a control system, or we can call this as an automation, right? And automation did not have very complex algorithm. So my controller algorithm, even some of these sensing and actuation components may be very simplistic, just relay with on-off control, or it can be complex with a pneumatic valve actuator, or it can be drive as an actuator. Sensors can be simply a signal, which is a temperature sensor, or flow sensor, or pressure sensor, or it can be nowadays very complicated, complex, say my camera, LiDAR, radar, and so on, right? So everything is can be submerged into it, and that is called a control system, or also called an automation. Right? And here we talked about the physical system. So this is these are cyber physical system, or we call it as nowadays also a term called IIoT, Industrial Internet of Things, because my sensors is not only signal, but it can be video, it can be camera image, it can be radar data, or say point map from the LiDAR, and so on. Okay? So that's where, and communication can be digital. My control algorithm or controller can not be only local, but it can be in the cloud, on the internet, at a remote place, depending upon the level of hierarchy. And that's where IIoT is also a part of the automation now. Right? So that's how overall system looks like today. But basically, system and automation, or control system and automation, is essentially this, right? Only the components keeps changing with the evolution of different technologies, electronics, computers, and internet, and so on. And the level of work have started, penetration have started growing. So earlier it was only simple equipments controlled. Then you went into plant level controls. Then it went into fleet level controls. And then it went beyond the physical systems. Control can be also in the communication. Control can be also into economics. Control can be in the pandemics, and so on. Right? So all these things have started spreading across. Anyway, I'll skip this slide here. Why feedback is required? So all sensing is required because of two important reasons. Because any of the basic system can be without disturbance, and will always have uncertainty. If these two are resistant, so feedback, the sensing and actuation through controller, that closing the loop is essential. That's what this slide is talking about. This slide again, I quickly browse through. We talked about Heron's door and flyball governor, right? So these are the mechanical automata. So these are the automatic control history, mostly last 50 to 100 years. How from these old automatic systems, Now we have motor-driven robots have started coming in. So 1928, first motor-driven automata was talked about. Unimed created a first industrial robot in 1961. Shiki is they mentioned about autonomous mobile research robot, which was in 1967. So these are the not new terms. People have started, attempted, but it's becoming more and more viable and popular last couple of decades. Right? Robotics is becoming very popular now, and it's very emerging also subsequently. So next few decades will be robotics and AI decades. Right? Stanford ARM, 1969. Right? This is a dexterous robot again, with electrical motor-driven robot and so on. So this is the first industrial robotic manipulator in Unimed in the General Motors. Right? That's where it was first time used in 1961 for the automotive and so on. I already talked about some of this draftsman, writer, and music playing instrument or robot, right? Which is still there in the museum. Okay. So with this very old history and some of the introduction of what automation means, my job will be easy now. Just quickly, we can go through different hierarchy and building blocks. So if you see, this is a schematic of a power plant. I am not going to talk in details about it, but basically, if you see, these are the different blocks highlighted in different color. So if you see the power plant, essentially what it is, this is a coal plant, coal-based power plant schematic. So you basically need a fuel and air, both have to be mixed together. They have to be ignited and combustion has to happen. This combustion generates heat, right? So from chemical energy in the fuel converted into heat energy. That heat is extracted or given to water. So water generates steam. From water you generate steam by heating it. So in any power plant, fossil power plant, what you have is fuel plus air, combustion of that. For combustion, you need proper air to fuel ratio for a proper combustion. If you have too much air, it's a less efficient combustion. So temperature will be low. If you have too little air, it will be incomplete combustion. So you might not come fully combust it. So C plus give you CO. So you have to leave it. C plus O2 proper combustion will give you CO2. But CO is something very harmful. So you need to get rid of it. So too much little air is also not good. Too large air is also not good. So you need air to fuel ratio control. That's one important aspect of any fuel-based combustion system. In power plant, you have a fossil power plant, you have a combustion system. And then you have airflow, you have steam, fuel flow systems. And then proper air to fuel ratio is to be controlled. And combustion happens in the boiler. Or in case of gas fossils, the combustion happens in the combustor of the gas turbine. Right? Gas turbine has a combustor as a component, part of this. Then steam is generated. Now steam, you need to extract that steam is actually having a thermal energy. The thermal energy you need finally to pass it through steam turbine to convert it into mechanical energy, right? So to rotate the turbine shaft. And this turbine shaft is where you couple the generator. Generator is electrical system, right? So you have air fuel, it's a chemical system, boiler, combustion or combustor is a chemical system, chemical mechanical system combination. You have turbines, which is again a mechanical system fully, and then coupled to the electrical system, which is a generator. And generator supplies power through substation and all. You just step it up and all, and connect it to grid, and it's connected to load. So based on load, now electricity storage is large scale, gigawatt scale storage is not easy. So any power plant, typically you require that generation has to balance based on the load requirement. Right? So if load is 1 gigawatt, my 1 or 2 or 5 or 10 generators, all generators in same location or multiple location across the geography, they have to combinedly pump the power of 1 gigawatt so that all the loads can be met. If you generate excess, it is not possible to store, right? And it may disturb your operation. If you generate less, then your load will not be met. So some of the load has to be staggered or switched off. So you need to have proper balance. And the loads are not near the power plant, right? Loads are typically through transmission system going to and distribution system through substations and it goes to the load, which may be local or it may be very far from the geographically. So grid might have multiple such power generations. So if you see, it's a system of system, right? So you have multiple systems collected together and so on, right? And ultimately your interest is load should be met efficiently, generation should be efficiently done. And for that, all the operations of different steps, because anything changes on the load side, it will basically change the current passing through the generator of the power plant. And generator of power plant will have different current. So back pressure, back force created on the turbine will be different. Now turbine is getting power from the steam. So my steam flow has to be changed, right? And steam flow has to be changed. That means my boiler, my thermal energy has to be balanced. So my coal and my fuel flow should be changed. And if as fuel changes, my air flow should be changed. So these are all coupled systems, right? So typically, any physical systems are having such large system of system with lots of coupling among each other. Sometimes coupling may be separable, sometimes it may not be separable. Okay? So basically, if you see, the automation is required at every level, whether when I'm looking into my airflow or that means I have a compressor or pump, a fan, which is pushing air, or fan which is sucking air. That fan has to be controlled, right, for changing the airflow. Right? So that is a system required. So I can measure the airflow and then control the fan. A fuel flow, coal. So coal flow, or if it's a gas flow, or oil, if it's a oil flow. So oil flow has to be measured and flow needs to be controlled. Who decides the set point of flow? Set point of flow has to be decided based on the power requirement. Or rather, power requirement will decide turbine steam flow requirement. Steam flow requirement will decide the coal flow, fuel flow requirement. Right? So this is all hierarchical connection, right? In a system of system. And all this level you will have a control, automation. For fuel flow, I will have automation system. For air flow, I will have automation system. Steam flow, I have automation system. When I do steam flow control, I should also ensure that steam temperature is enough, because if my steam temperature goes low, steam will condense. I don't want steam to get condensed in the multiple stages of steam turbine. So steam temperature has to be maintained. At the same time, when I want to maintain temperature at a higher pressure, because I need high pressure steam, then I can have lot of amount of work can be done, right? So if I want to generate more power, I need a high power, high pressure, high steam flow, so that I can do more work, right? And for that, doing more work, I need higher amount of temperature and a higher amount of pressure and flow rate of steam. And steam to be maintained at a higher pressure, I require boiling point will increase, right? You know the steam tables. So higher the pressure, steam boiling point will be higher. So temperature has to be higher. So temperature control, flow control of steam, they are coupled. And all these things requires a control loops or automation system around those. So all these automations to loops or systems, they are actually in tandem, working together, right? Collectively interacting with each other. So if you see the typical industrial scenario, this is how you will have multiple components playing a role. So this slide, what I'm talking about is the same. This is called a Purdue model or hierarchical control system model. So if you see typical, so I gave an example of a power plant here, but same thing applies also to refinery or petrochemical or chemical plant also. So your process plant, where your field instrumentation layer, where you may suppose it's a refinery. So your crude which is coming in, crude is a feed to the refinery through distillation column. Distillation column is there is a series of distillation column. So each distillation column will have some separation operation point. So initial distillation column will separate out the lightest component in the crude, right? So gasoline, then petrol, then diesel, and so on. Then finally heavy oils will remain. So different series of distillation column with different operating temperatures and pressure, they will separate out different components from the crude. So it's a refinery. So all this field will have multiple systems, right? It's a connection of system, interconnected system of system with all amount of coupling interactions amongst them. And you will have field instrumentation layer, as everyone requires automation. So they will have sensor, controller, and actuators, and so on. And in a typical, say, power plant, you might have 40, 50 control loops, right? In a coal plant or gas plant. But if you talk about refinery or petrochemical complexes, you might have maybe hundreds of control loops, 500 control loops, right, in that. So all those are connected. So you require a level 2, which is again a regulatory control. So mainly plant operators are sitting in this control room, and they have a distributed control system or PLC and SCADA based system sitting in the regulator control layer. So all data from the field actually is transmitted through digital or analog communication. Earlier days, pneumatic communication, electronic communication, but nowadays it's all digital communication coming to control room. So it's a large complex, right? Power plant or refinery or chemical plant will be few hundreds of meters wide and long. So you can't have person going controlling everywhere. Earlier days, maybe 100 years back, people were controlling local. But as I mentioned, human tendency to get rid of repetitive tasks. How can I do job more easy? Sitting in the centralized place so I can see everything. So those things evolved, right? Human tendency, we started building better and better automation system or control systems. And now we are able to do operations from the control room. Again, higher up that earlier, say regulatory control layer, human operator were doing it manually, right? So they will look at the plant, get all the data there in front of computer or controller, control system screens, monitors, and they will decide the set points and command it. But then again, as remember the tendency of human, can I get rid of, why should I keep sitting in the control room and keep watching all the parameters and decide what should be the set point? It's a repetitive task, right? Or it's a tedious task, cumbersome task. Can I have something else? That's where dynamic control layers started coming in. So with the, say, process control computers and SCADA, some of the tasks can be programmed now, or some of the higher level work you operator can get rid of doing. So you have then model based control, model predictive controls. Those kind of algorithms started coming in, and those started making this layer again automated, right? Earlier, and then earlier above that, some settings of this dynamic control layer or optimization layer automation were decided manually. Then people started looking, can I have real-time optimization, steady state optimization of my process if I understand, mathematically represent them? Can I do optimization instead of human has to see so many parameters. He can't decide what is the best set of parameter. Can I run the optimization algorithm in a process control computer or a computer at this layer? And this computer can have my steady state models of interdisciplinary interacting system of system. I can have a mathematical model. This can be mainly linear programming, quadratic programming kind of steady state optimization solution, which can be done in the computer, and that can guide the parameters. So human operator doesn't have to take those decisions. So automation started from very field layer, simple physical system controls and automation to regulatory layer, then dynamic control layer. It started coming into real-time optimization layer. But then planning and scheduling job were also done, were earlier done by management. So by planning and scheduling, what is meant is, suppose it's a petrochemical plant or a power plant, how much I should produce, right? How much I should produce, when to produce what, right? So if it's a high density polyethylene, same petrochemical complex is producing, say, HDP, LDP, LLDP, different polymer grades of HDP, different polymer grades of LDP. How those things can be, should be produced when, that is a decision, right? Over a month. So based on the marketing or salespersons provide data, next 1 month, I need 10 different customers. They need HDP grade 1, HDP grade 2, LDP grade 5, and so on. And we require to supply those products to these customers within next 1 month. So before so-and-so deadline. So plant has to then management layer in the plant operational management layer. People, they will actually do this, they will do this calculation, and they decide what is the optimum way with minimum wastage. I have to change the grades of the product in such a way I should plan which product to produce when, which grade of product to produce when, so that I meet all the customer requirement in such a sequence that I minimize the wastage, because between grade change from grade 1 to grade 2 or grade 2 to grade 5, I will always have a wastage. So can I minimize those wastage? So how to plan this? So plan and schedule my production, right? So how to do that? So those jobs were done manually earlier. Afterward, though it was with a computer aided, but it was still done manually, like a control room. Operator was sitting, but he was deciding. Similarly here, you do Excel based some tools built, but manager has to do those planning and scheduling. Now that's where also supply chain, lots of optimization layer has come through SAP enterprise layer, ERP packages, right? So automation has started playing there also to make human life easy, to do all this number crunching and make a better decision with a computer doing a job better than human can do, right? And human also has a dependency. So different people will plan and schedule differently based on their experience and expertise and thought process. So all those consistency can be also brought in if it's automated. Subsequently, it goes also to the supply chain layer. So say this is a petrochemical complex. So raw material of petrochemical complex comes from the refinery, right? And raw material of refinery comes from the oil field. So these are all connected, right? So it's a system of integrated plants. So can I have a supply chain also brought into my automation layer? And those are the things which are happening in the computer layer. Supply chain optimization or supply chain management. So earlier supply chain management was done manually, though it may be using computer, but all data is in computer. Manually decisions are made, or they will crunch the numbers, different scenarios, do scenario optimized simulation, and then decide. Experts, supply chain experts will decide, and then he decide to meet this my production demand for petrochemical complex, how much I should produce, how much I should source, which grade of oil from which particular source supplier, right? Supplier 1, supplier 2, supplier 3, they are supplying me different kind of crudes. So what crude at what quantity I should pull from which particular supplier, when. All these decisions also started becoming more and more automated. This is where industrial automation has moved. So all hierarchy now automation has started penetrating or has already penetrated. Now, what are the building block of this? So if you see all these layers, these are the building block, right? So you have sensors, data, controllers, then actuators, and also the computer system, control rooms. These are the different subsystems or components. And communication. So here if you see field data comes in through the field bus or 4 to 20 milliampere analog communication, current communication. 3 to 15 psi, olden days it was a pneumatic communication, right, for the signal. Then it started becoming Modbus or field bus, Profibus. In automotive, cars and all, they use CAN bus and so on. So there are different communication layers. At regulatory layer and optimization layer, you have OPC, OLE for process control in the process industry. That's a popularly used protocol for the data communication. Right? From this layer to management layer, which is planning, scheduling, and supply chain, you have manufacturing execution system, which has a data communication. Right? And this was the hierarchical control system which I have shown here at different layers of industrial hierarchy or production control system hierarchy. It has again subsequently went all the way up to cloud now, right? So data goes to cloud also. So cloud will have a multiple fleet-wide monitoring. So plant 1 doing my petrochemical complex 1, petrochemical complex 2 can be in a different geography, right? In different country also. And then my corporate management can be sitting in one place, and they can monitor all the different supply chain and production plants all together from a management dashboard sitting in the corporate layer. So but they don't need to see what is the temperature of particular things and all, right? So at different layer, the data communication will be filtered out, and only key information will be sent to the upper layer and so on. And some of the historical information will be there in the different layers, so that it can support the decision making in a better way. So this is all are the different building blocks of enabling this whole hierarchical production system, industrial production system, which can be process industry, it can be power plant, it can be manufacturing industry. I'll briefly talk about that and so on. So now if you see what are the evolution of the building block, which has enabled more and more advancement in, see, the concept is similar. Earlier it was a pneumatic control system. Many of us would have seen, those who are old timers, we have seen the pneumatic controller. So you talk about PID control. It's not only software. Today it's a microprocessor based or computerized software. But before that, there were electronic PID controllers, right? Controller module, which is a small electronics box. Before that, it was pneumatic. Now, pneumatic, you can say, how can I crunch the numbers? But pneumatically, you can calculate, do integration. You can do, say, multiplication. All these mathematical operations can be done pneumatically, but through air signal, right? By using flapper, nozzle, and some of the bellows mechanism. Similarly, hydraulics also, you can do all this computation. Before that, even mechanical linkage can do using some damper mechanisms and all. You can do some of this basic computation. And early days, you're like flyball governor, you can say it's a proportional controller, right? Because lever mechanism is a gain, right? It's a gain mechanism. So gain is what? It's a proportional controller. So those devices were there, but now measurement has started changing. So before 50s, say pneumatic systems and all, right? So all the sensing was through pneumatic transmission from field to control layer. Then you have started getting the analog and digital electronics, including smart functions built into microprocessor-based systems and so on. So they have started becoming smart. We call it as smart transmitters. The transmitters are actually measurement devices, right? Not a transmitter, the communication. It's still a communication, but communication of the field signal, right? Which we call it a IoT. But IoT exists in the process industry, maybe 30, 40 years old, right? It's not new. Only cloud penetration to cloud and entry of internet is happening now. So it's a two ways. The internet earlier was only at the cloud layer and hierarchy level up at the management layer and up to say control room. But not internet was not there in the field layer. But now that is penetrated there as well. So that is one. Other thing is, as I mentioned earlier, it was only signal, temperature, pressure, flow, different say pH, conductivity. Those are the sensing signals which you were measured. But now you started becoming more broader. So you not only have only signals which are measured, but multimedia sensors have started coming up, right? So you have now camera integrated into system operation for a betterment of operation, right? So through signals you can achieve only something. In addition to signals, if I also put cameras, CCTV, it has become very common, right, for monitoring the operations in any even households and so on, right? So similarly in industry, it has started penetrating. So after 2000s, you have different kind of evolution here. So from pneumatic, analog digital electronics with microprocessor based, so they are smart, microcontroller based and microprocessor based. Now it has started becoming wireless because Wi-Fi, Bluetooth, and then cellular technology which is coming, LoRa, radar technology is coming in, and so on. So sensing itself has been wireless or through camera, right? So camera, radar, you don't need to contact, right? So you can have camera which say IR camera, which can give you what is the temperature of the surface, right? Which is the hot surface. So without contacting, thermocouple or RTD and all, they have to be in contact with the body for which temperature is to be measured. So sensors are becoming wireless. Communication also started becoming wireless, right? Instead of 3 to 15 psi, 4 to 20 milliampere analog signal, or digital communication, there also you need a bus. TCP/IP also you need a bus. But now communication has started becoming wireless. They are becoming more and more smart because computers are there available at a higher level. Computers are becoming cheaper, or they are becoming electronics have started becoming more and more compact, and so that they can be placed in the field more and more robust. So lots of number crunching can be done at the lower level also. And of course, multimedia sensors, as I mentioned, you can have LiDAR, or you can have radar or camera, all this becoming part of the sensor. So measurements have started evolution of measurement is right from very basic, simple pneumatic, hydraulic measurements to electronic measurement with microprocessor, microcontroller based measurement, which have started becoming smart, to all the way now wireless, smart wireless based, AI based, multimedia, IoT sensors. Coming to next, controllers, how they evolved. So 1970s, you had a pneumatic controllers, mechanical based controllers, hydraulic controllers. Becoming now 80s, you have seen this electronic controllers, right? There's electronic, analog electronics with, of course, in between you are even valve based electronics, but Here what I showed is transistor-based electronic instrument, right? Controller. They started becoming PLCs in 90s, 80s and 90s. PLCs started coming up. PLCs grew up further. Earlier PLCs were only sequence control. You can do only digital signals. But then analog signals and analog control algorithm also started building up inside PLC. They call PAC, programmable automation controllers, with HMIs and so on. And future now, complete architecture of controllers, embedded systems are changing. Instead of PLCs, people have started moving towards more and more industrial computers with high-end computing power available, and do edge, which is called edge computers or edge devices. And you do cloud connectivity and do some computation, partial computation can be on the edge, some can be on the cloud and so on, or combo based on the hierarchy and so on. So basically, this is the evolution of controllers happening over last many decades. Distributed control system, olden days, 70s, this is the kind of distributed control system inside the control room. Yokogawa Centum CS system, which was in early 70s, right? So it was electronic controller with some basic computing power. Because 70s computers were in existence, but they were large scale, large sizes, room size computer, right? And you had say printing tape based and this printing based computing. So program can be on the paper, right? Paper punch cards and so on. So some of you might have seen magnetic tape based, even I have seen those computers. And then 80s, it started becoming more and more computer savvy, right? So your control room, this distributed control system, where lots of crunching is done in the operator station near the control room or in the panels in the control room. So this is changing like this, and now control systems or distributed control systems are also scattered. So it's not only in the field, but also in the cloud and combination of this. So this is where it is moving. Control room, how the control room has started changing because of all this evolution in measurement system, evolution in controllers, evolution in distributed control system. The control rooms themselves have started looking different. So earlier, if you see 40s, these were the lots of strip chart and circular chart recorders in the pneumatic or very simplified electrical controllers. And then your slightly better electronic control rooms were still large, right? Compared to this, they are smaller. Lots of data on the control panels, and control room operator sitting in front of that. But job of operator is still very complex because he has to see so many screens and data and indicators and chart recorders, strip chart recorders, and so on. Then they have started changing with the full computerized control rooms, right? Where lots of data is coming in the screens, and screens can be modified, changed, and so on in the computer screen, right? Simply monitors, right? Your LCD monitors and so on, including touch screen and so on, which has started coming in. In future, you're talking about 6 sense and so on. So these are the touch screen, not even as monitor. It can be any device. It can be on mobile. So you operator can be even flexible, movable, right? So dashboards can be on the mobile based on the different admin level of the management or engineers. And of course, you can create the HMI screens or user interfaces on the wall just by projecting those and so on. So this is where the world is moving. Evolution is happening. Control schemes wise, I already talked briefly about this. If you see, you earlier had a very simple on-off for PID controllers where number crunching is done in the controller. In case of all the physical system, the controller is nearby. It can be pneumatic or electronic or microprocessor based. You can have a basic simplified algorithm which can run on this. So single loop and multi-loop controllers for running and most popularly used control algorithm is PID, which is very versatile. And still at field level, lower level, almost 90% of systems are having a PID controllers, right? And maybe on-off controllers, some. Multi-loop controls, feed forward, cascade, ratio control. Some of these complex control schemes are part of this control schemes, right? Earlier. Now, with use of computers, now because you have more computing power, more number crunching, you can go with high-end computational algorithms for the decision making or controller, right? For the control algorithm. You have multivariable number crunching through predictive control, optimization based solvers you can have in the computer. So you have say model predictive control, which runs the model, does the simulation of model, predicts the behavior of the plant or whatever is the control signal, your behavior of that next maybe up to next settling time for the system, right? During the say next 5 minutes, 10 minutes, or half an hour, depending on the type of system, and take the decisions to minimize the future errors by running real mathematical solvers, right? Optimization solvers. Optimization solvers are iterative algorithms, right? Through numerical computation. And those can be run on the computer that cannot be easy to run on the microprocessors. All right. Of course, nowadays, edge computer boxes, they are having enough computation power. So you can even run simplistic computation algorithms, including some of the solvers, right? Optimized solver up to certain size of the problem. But size of problem of the refinery or big process industry with hundreds of variables, you cannot run them in the embedded systems. So those higher-end computer schemes, with the evolution of those computers penetrating into the control rooms, now these kind of complex control schemes have started evolving in use. That's a supervisory layer. That's called a supervisory layer, right? In dynamic optimization, steady state optimization, production planning, and scheduling layer, you started running lots of decision-making algorithms. And those are part of the control schemes now. Right? Those are the control schemes at the supervisory layer. You also need some places non-linear controls or robust controls based on the kind of algorithm. With the bioprocesses, you need more robustness because basic system behavior is not very well understood. So mathematical models are not very accurately known. And those are the systems where you can do this kind of number crunching. So control schemes have started evolving from basic simplified control schemes running single loop and multi-loop, some control algorithms, simplified control algorithms, to complex control schemes, right? Where some of these control schemes I'm showing here is we use in some of my cement plant work when I was in my own experiences. So we built cement plant kiln and ball mill optimization. It's a control system running in the control room in a computer. Computer pulls data from the DCS and downloads set points to the DCS. So operator has to just watch. He doesn't have to make decision to download the set points. And operator earlier, when they used to do the set point operation, they could not do every minute to minute, right? So it's a human limitation. So operator would change set points maybe infrequently, and maybe once in half an hour or whenever needed. When he sees, oh, here I should take some action or something is alerted, he will take action. Otherwise, he will take action maybe very slow rate. We used to decide set points by using MPC algorithm, running sequential quadratic programming, which is optimized mathematical optimization algorithm, using the mathematical model of my system, ball mill or kiln, cement kiln, using some of the soft sensors. So some of the quality parameters are measured in the lab. So this lab measurement comes every 2 hours or 3 hours or 4 hours, depending upon the frequency of measurement. But I need to decide set points every minute, right? And change the set points every minute to minute. So we used to have a soft sensor, and soft sensor will be based on the model. So we had a measurement system, which is a software, controller, which is a high-end control scheme, which is a model predictive control, which is using model and optimization algorithm, and using data from the soft sensor and some of the parameters and tuning parameters of the algorithm itself, and decide the set points. We download it to control room, and from control room it goes to the planners. Right? This is the scheme of MPC. I will not talk about how MPC algorithm works because that's a different subject topic, so I will not cover it here. It's a detail. But this is the kind of control scheme we use, and we could show that by doing this, we could improve. Because see, whenever we do any evolution, it should be for some purpose, right? So it's not just for fun or academic purpose. So there should be some business case, then only people will use it. So we could show that I can get better energy efficiency in a ball mill, I can get better fuel efficiency in the cement kiln, and benefit were of the order of, say, ball mill, we could show that it can be up to maybe 7 to 10% better power consumption or lower power consumption. And when we talk about power consumption in megawatt scale, this is a big number, right? So in terms of monetary, it can be lakhs of rupees of numbers, which is a saving for the plant. Getting the same and better quality. At the same time, you get a better quality because it's a soft sensor which is estimating the proper quality parameter and adjusting the controls at the points based on that in a minute-to-minute basis, rather than operator waiting for lab data to come in and then take a decision after 2 hours, right? Then quality variation will be more. So we could tighten the quality better. So give better quality consistency, minimize the power consumption of the ball mill, right? Or fuel consumption in the cement kiln. We could save fuel consumption by 1 to 2%, right? Which is a huge number in an annual basis, if you see. And then algorithm is just a software, right? Sitting, pulling data from the DCS, which is already existent, running this algorithm on the computer. So you just need to invest a computer and this whole development and then get this advantage. So benefits of this kind of high-end algorithms, control schemes, have been a motivation for that, has been a business benefit, right? And better quality, better performance of the overall operations at the higher and higher level. Now, I talked about this high-end control algorithm. This was left side, what you see is the automation building block for the continuous process, which we have deployed. This is something which is deployed in the cement plant. So we had, as I mentioned, we had a control room, right? So field control data from the plant, from the cement mill, ball mill, vertical roller mill, and kiln, those data are coming through PLC, different sensors and all. It comes to the control room. From control room, what we added in the hierarchy was a dynamic and steady state optimization layer. So OPC, as I mentioned, OPC is only for process control, communication layer, pull data from this DCS or PLC system to my computer, and computer has this kind of schematic. I already talked about soft sensor, predictive control, optimizer, this as a schematic. But this is still a hierarchical, right? So data was coming through OPC to here, and then this was doing number crunching in a computer, and this computer is connected at a higher level with the production planning, scheduling, and so on, right? Which is at the ERP layer through MES layer. Now, this is the control room for that. But now what is happening? Your field instruments. So here, field communication is a different protocol. It's called a operational layer, operational protocol, operational communication protocol. So field bus, Profibus, signals 4 to 20 milliampere, or digital RS485 based bus, digital bus, having Modbus protocol or Profibus or CAN bus protocol. All these different protocol, they are called the industrial protocol or operational protocol for the control system. Higher level, what you use is a internet protocol, because there you have computer networking. So once you data is coming to computer, upper layers are connected through computer, and computer networks are already existent at the upper layer. So which is called an IT network, right? Internet network or computer networking. So field side, you have communication protocol, which are completely different, and it is for the purpose. So because internet protocols or computer networking protocols were not deterministic in nature, which were risky to use in the field layer, right? But now what's happening is field devices are becoming smarter and smarter, with more and more embedded system penetrating into system in the field layer, with more and more smarter miniaturized microprocessors with high computing capabilities in a single small device started becoming happening. So those computing devices can handle computer networking also. And that's where TCP kind of IP networks are penetrating into the field layer also today, right? So field instruments are becoming more and more popular with the internet protocol. So internet networking has started penetrating there. So this is called, you might have heard the word IT-OT convergence. So IT layer, operational technology layer of communication, they are coming together now. They are actually, difference is merging. Earlier they were separated, and that's how plants were operated. And of course, there's always a risk for the plants, any production plants, to connect to cloud, because they don't want to expose the data to the outside world, because there are always a risk of data safety, data security, at the same time also risk of cyber security, which is becoming more and more, people are becoming more and more aware last 1 or 2 decades, right? Because there has been a lot of attacks on the plants, power generation, or even refineries, or power distribution or transmission systems, right? So future wars, as you know, will be becoming security based. So you just attack the cybersecurity critical infrastructure of any country, and that will be a huge loss for the country, economic loss for the country, huge harassment for the people, and that's how the wars are being fought or will be fought as we move into future. So those were the worries. So typically, industry plants, power plant, manufacturing plants, they don't want to connect. They want to be air gap from the cloud, or connect only IT layer, and there is a separation between IT and OT layer with different secure cybersecurity mechanism. But now with the more and more penetration of say cameras into field, different smart devices into field, though it's a signal, but they are smarter. So IP networking, internet connectivity has started coming up through IoT devices in the field layer, and that's where world is moving or evolution is happening. And this is the I'll talk about that subsequently. This slide is a actual survey report. I little while back I talked about benefit. What is the motivation of higher end control schematics, right? Model predictive control, AI based control, or robust controls, and so on. So there was a survey done. There's a published paper in 2008 in process industry. Survey was done in IFAC body by some IFAC Journal of Process Control, one of the very leading process control journal from elsewhere, actually managed by IFAC, International Federation of Automatic Control. They surveyed and they found these are the different customers of this advanced control schemes, and they their report outs. What is the benefit of advanced controls, higher level automation they found, and this is like oil and gas saw the maximum benefit. Some of the numbers are refining complex, some refining complex, 1,500,000 euros was a saving in a year because of better automation at the higher level. Similarly, lube oil plant, 1,300,000 euros was the saving for them. Similarly, hydrogen plant, 250,000 euros was the saving. Electrical power plant, 125,000 euros was the saving. These were the customer data, real customer data. Okay? So these are the kind of benefits they saw. What is the type of benefit they saw? This is the second slide, again from the same survey report. Say majority of them saw throughput increased, stability is improved, energy consumption is reduced. I also talked about cement plant and all, right? So it's my own experience, cement plant. We could show that benefit. Even throughput increase, we showcase in the cement plant, we showcase the benefit. But the survey report is talking about all this process industry. And they saw this kind of different kind of advantages they have seen through the hierarchy based automation penetrated into different layers of industrial control system or industrial automation layers. Right? So these are the different benefits. I will not talk about each and everything, but this is where it has been motivation. With this, now we come to the third part, which is emerging trends. So we'll talk about some of this. I already conversed or we talked about or discussed during previous slides. We'll just quickly talk about that. So one of the emergence is after seeing the benefit, typically process industry hierarchical automation started early, maybe 2-3 decades back, 3-4 decades back. 80s onwards, they have started seeing process control layer. After that, even production planning and scheduling layer and so on, and supply chain optimization. So they started seeing more and more benefit as presented in the previous pages in the report based on the survey in 2008. But slowly after seeing those benefits, what is happening is automation is now penetrating different industry. Right? So process industry, of course, we talked about, that is the first taker. And it was natural because process industry typically are having a slow behaving system. Right? So there is enough computational need are slightly lesser, and the computer in 80s and all, computers were still slower, right? Today's computer versus those computers. So applications of those started penetrating more in the slower behaving system, which are in the process industry, chemical plant, refineries, and so on. Compared to, say, automotive, mechanical manufacturing, gas turbine, which is a fast mechanical rotating machine, or aircraft engine, which is a fast rotating machine. So where need of control actions is very fast, compared to process industry. So process industry, cement plant I mentioned, we could take supervisory decisions every half minute, 1 minute. In kiln case, we took decisions every 2 minutes and so on. At supervisory layer, my lower level control will work at 4 or 40 millisecond rate, sampling rate, but higher level will be at a slower rate. But those slower rates were not possible for the aircraft engine and those kind of systems. Or even power electronics is an even faster system, right? They are into millisecond scale. You need to take this. Because 50 hertz frequency power converters, it's a 20 millisecond, one cycle, right? So if you have to decide IGBTs or control thyristors, you have to take a decision at a very faster rate. So all those things are slowly penetrated. Seeing the benefit in process industry, which I talked about in the previous slides based on the survey, different other industries started interested, and it started happening with the betterment of computing devices, better and better computing devices, or more and more advancement in the computing devices and embedded computer systems. Use of this advanced automations or automation at the higher levels to minimize human intervention there for a betterment of the performance started happening. From process control started also into manufacturing industries, energy and environment, power generation, gas turbines, and so on. Model-based controls in the gas turbines, model-based controls in the wind turbines, manufacturing industries, automotive is a big example, but machine-to-machine controls. So machine controls are through CNC machines and so on, right? We quickly talk, we know that. So those things have started penetrating, but higher level controls have started penetrating in automotive industry now in a decade or maybe 1 to 2 decades. Process industries happened maybe 4 decades back. Large scale distributed utility industry like water and wastewater systems. So which are distributed across geography, right? Wastewater plants or different industrial wastewater, utility wastewaters and so on. So they started getting interested. Similarly, building automation. Today's more and more smart buildings have started coming in. Large malls, large airports, large say seaports, and so on. So all the building and infrastructure systems, automation has started penetrating there also for the better energy optimization. Right? Again, for the benefit of reducing the global warming. Because high volume air conditioning systems, HVAC is a very high energy guzzlers in the large scale buildings, centralized AC system, which we talk about. So in large mall, large residential complex, large commercial complex, large airports, this is where more and more automation started penetrating. So basically automation started expanding beyond the traditional use cases where it restricted earlier. That is what has started happening. Automation started happening in infrastructure and logistics. We all are aware of even car booking, right? So Ola, Uber, it's automation playing at that level, right? With not fully autonomous, but it's giving you lots of operations. So it's again, remember that earlier need of automation is based on human wants to make his life easy, want to get rid of cumbersome tasks. So from mobile, you can book the vehicle will come at your doorstep and so on, rather than you going and searching for the vehicle, right? For auto in maybe two decades back. So this is where the world is moving. Automation is penetrating across. Now this is one good slide. I will not talk about all different revolution, but if you see, there was different different revolution era. So if you see 1770s, so on the bottom chart, okay, let me put. So if you see here, there's maybe every revolution has been maybe of 8 to 10 decades, right? So 1770 to 1853 to say 1900, 1870, 80 is a textile revolution. Then railway revolution came. 1800 onwards up to 1900 was a railway revolution. Then automotive revolution, Ford Motors, cars, right? Diesel engine, petrol engine, and so on. So all those started. So say 1900 to almost 1970s, 80s, and so on. And now they are established. Next is the computer revolution. Then next was a agent-based and grid revolution, which started happening. Right? Connectivity of the different electrical grid system. Then started coming nanotechnology, hydrogen, fusion, IoT revolution, which started 1990s onwards. Internet was first good use case or formal use case of internet for the commercial and human normal people. It started earlier with the defense application, but actually started happening. Bill Clinton, you can see the Bill Clinton and Al Gore famous picture, which is net day. So first internet they installed in their office. This was in 1996. So after that, internet revolution started, right? And with internet revolution, Internet of Things which started coming up in, and that's the era. So currently we are in the era after 1990s, 95, 2000. We are in the era of IoT. Right? And this is where, and then with each revolution era, things are changing and evolving, and which is making a benefit in every field. So all these technologies are benefiting to different systems, including automation systems also. Discrete manufacturing, as I mentioned earlier, automation started penetrating beyond process industry to manufacturing industry. So if you see today's manufacturing plants, automotive plants or machine manufacturer, which are called the discrete manufacturing. So process industry, chemical, fertilizers, petrochemical refineries and petrochemicals, they are called a continuous manufacturing. Power plants, they are continuous manufacturing plants, right, or production plants. Whereas automotive are countable, right? So you manufacture 100 number of units rather than how many kilowatt of power or megawatt of power or how many quantity or flow rate of products for polymer, how many tons of polymer. Those are continuous industry or manufacturing. This is called discrete manufacturing. So similar hierarchy which we talked about has started happening or is happening last couple of decades in manufacturing plants also, which was not possible earlier, right? Which was not thought earlier. So chemical plants, refineries and all, it has started happening in 80s. Whereas in manufacturing industry, it started coming in 2000s era. So cell level manufacturing, which was existent, shop floor, cell to cell floor level, existent, different levels. Factory level started happening with connecting different shop floors, interacting together, coordinated work, job. So assembly line, getting data, getting components from different manufacturing supply cells, and those supply cells will produce, and those parts have to be assembled, and that's how your factory level work started happening. Enterprise level, again, inter-enterprise level, supply chain management and so on. Enterprise level planning and scheduling solutions. So this is how the similar hierarchy layers have started coming up in the discrete manufacturing also. With this happening, right, with all this evolution of measurement systems, controller systems, control algorithms, or control schemes, actuator mechanisms, communication between different devices and machines and systems, started happening more and more automation penetration into mechanical manufacturing or discrete manufacturing industry. And if you see now discrete manufacturing industry evolutions, this is where industry 1, this chart might have been already covered by some of the previous speakers also. I would definitely see because this is the industry 4 workshop, right? So if you see the evolution, industry 1 workshop, 1 era, end of 18th century, which was first mechanical loom, right? Hand loom with some mechanization to make the job of textile or doing the weaving easy. Industry 2 era, first production line, slaughterhouses, they started having some mechanization of manufacturing or production. Then started coming program PLCs and all. They started in use with some simplified robots. Before that, CNC machines in between, right? So CNC machines are programmable machines, but they were all still a single job. So this robo arm or CNC machine will do single job. They can do multiple tasks, right? Single machine can do multiple tasks, but they were doing single job and singularly. There were no coordination between multiple of these machines and so on. Industry 4 is the era where you talk about all these machines are getting interconnected now. Data will be possible to communicate amongst this These are machines are also connected higher level with hierarchy. So it started getting IT/OT layers connecting together, right? As we discussed earlier, similar to process industry. So that's what is coming. We also call it a cyber physical system. So cyber system, which is the internet connecting with the machines directly, right? Or some of the sensors on the machines directly, or with the transmitters, measurement systems directly, or actual systems directly. So IT OT conversions has started happening in the mechanical manufacturing industry as well. And that is the era of Industry 4. And Industry 5, you might have heard about. So is where people are talking about how human and robots or these machines, automated machines, can very seamlessly or very smoothly work with the human. So you talk about cobots, right? So earlier industrial robots were isolated. Human were not allowed to go nearby. But nowadays you have a cobots. We are collaborative robots, which can work along with human together. And so in the plant, robot will do some of the tasks, but some of the intellectual tasks, human presence are required. So human can do some of the tasks which are slightly complex for the robot to do because of dexterity and some of the human advantages in doing some of the tasks. So can human and robot work together so that you can still benefit with the automation, right? And that's where Industry 5 will come. And then for doing that, you need you also talk about cellular communication through 6G and so on. So machine to machine data communication, coordinated work between multiple machines. So 5G is started penetrating in Industry 4, but 6G will come with even higher data latency, very faster data latency, and higher scale of data, volume of data. That will be possible in 6G. And with that, Industry 5 will have those technologies penetrating. I already talked about this slide in the previous. So this is left side. What you see is a hierarchy, which I already talked about cement plant, right? So field layer and my upper layer, supervisory layer are isolated. OT and IT, which are different. But now you have this PLCs and all, they are being replaced by embedded edge boxes, which are actually high-end PCs, industrial PCs, with 5G or cellular connectivity or Wi-Fi connectivity. And they can directly talk to cloud. Or also on the edge, so intermediate in the plants, you might also have on-prem servers. So data can be through server to cloud, or it can be direct. Some of the data can be direct to cloud, and so on. So these are the kind of hierarchy or architectures change which are happening. And with this, it will having need of IT/OT convergence. And once internet is penetrating into the field layer here, to the field level, there is a more concern about the cybersecurity, because these are all critical tasks done at the lower field level. Anything happens, because they need a fast latency of operations. If any cybersecurity attack happens, your whole plant, automotive manufacturing plant, can be stopped, right? If there is a cyber attack, my machines itself will do maloperation, or it can be stopped, and then there will be shut down for a day, 2 days, whatever. And because of that, there will be huge volume power production loss, which is a huge economic loss for the industry. And through that, through industrial loss, it's a loss to country, right? It's a GDP loss, economic loss to a nation. So that's where it's happening. And this is why cybersecurity is becoming more and more important nowadays, because of this IT/OT convergence and internet being penetrated all the way up to industrial control system layer, at the field control layer, and so on. And that's what we call cyber physical system, or industrial internet of things, or internet of things, or medical things, and so on. So IoT, people have started talking about different IoT, those different words, right? But they are all talking about same, basically applied to different domain. In IoT era, so factories are changing, we already talked about, right? So right from top, unconnected machines to machines which are connected with through sensors, data is coming, human is able to monitor them. Then interconnected machine, some of the tasks done collaborated way on their own, some of the tasks are done in collaboration with human, and so on. And then slowly it's going towards globally connected plants, for better supply chain and collaborative manufacturing and so on. And these is the things which are happening because of this changing. This is where factories are changing in future. And all this is going to have a benefit. So this chart is giving what will be the industrial internet, IoT, impact in the different geographies, right, in the world. So these are the, so if there is no IoT, the this chart is slightly busy. I will just talk about one point here and then we can move forward. So you see here, 2030 baseline, this is where the projection, the billions of dollars from 2005 to this is the kind of investment and benefits in GDP in different Asia Pacific region, North America region, Europe region, and so on will happen. And those are the numbers here. And this is the baseline up to 2030. But that baseline will change, will shift, right? If there's because of the industrial internet. So baseline is changing, and then those changes are, if you see, if here in the world, globally, it's a 15.3 trillion number. That's kind of a benefit which will happen in the manufacturing industry or in factories collectively across. And geography-wise, these are the numbers: $4 trillion or $6.5 trillion impact of IoT in the baseline numbers, baseline GDPs of the countries. This is where the growth is. So that's why it's of interest, right? So why any technology becomes more and more popular, or why it's becoming more of industrial interest? Yes, it's bringing economy, making it better. Life is becoming better, and economics-wise is becoming better. So it's a viable. Otherwise, any technology which might have technically correct, it's doable. But if it does not bring benefit, nobody will adopt it. Right? So adoption happens in industry or by human only if there is some benefit. And this is where IoT has a big benefit or impact, and that's why it's becoming more and more popular. And IoT era of smart factory, this is just a picture I visualized. So these are the different types of work is happening. So with all this data coming into higher and higher level, from the field level to higher level, you started also talking about different other things. Can we do predictive maintenance instead of time-based maintenance? Can I do condition-based monitoring and maintenance, right? Factory environment monitoring. So in addition to my machine, can I also monitor what is the factory environment? What is the temperature in the factory? What is the energy consumption to maintain the temperature? See, many of the discrete manufacturing plants are actually air conditioned, right? So they are energy guzzlers. So in the shop floor, you will have air conditioning. So you want to also monitor the energy, and energy monitoring, energy consumption of the HVAC system depends upon the actual environment monitoring in the plant. On the shop floor, you will have machines as well as human operators. So you need to maintain the operation environment comfortable for the human, for their operation to be more efficient, along with the machine. But at the same time, you need to operate those HVAC system more efficiently or more optimally. And that's where energy optimization, environmental optimization of the factory floors, similar to like building and infrastructure automation, has started happening, right? And similarly, testing has started becoming autonomous because that test data has to be integrated. Now those plants of these different machines connected now are moving towards more and more robots. So right side, if you see the picture of a plant, discrete manufacturing plants, which has more and more robot and very less minimal humans or no humans, right? And this type of plants are happening also now in India. I'll show you one video of Mahindra plant, which is moving towards fully autonomous plant in the automotive.
Excuse me, sir.
Yeah.
Sir, we are already running actually out of time.
Okay.
So can we take 1-2 questions from audience?
Yeah. Can I just quickly cover these 2 slides and then we will come? I have only 2 slides to cover, which I'll just talk about, and then we can take the questions.
Yes, sir. Yes, sir.
Okay. So give me just a few minutes.
Yeah.
Okay. So now other penetration is in now robotic and automation is penetrating beyond industry floor. And that's what this slide is talking about, right? So your industrial robots we talk about lots of things about the industrial robots and all, and automated machines. But now, robotic machines and automation is penetrating to surgical robotics, human help, right? For the old age ladies or old age people, you have human health. So humanoids have started coming up. You have worm robots, snake robots, insect robots, drones, which are becoming very popular applications across different application areas, which are even non-traditional areas like agriculture, oil rig inspection through UAVs, wind farm inspection through UAVs, AGVs on the mobile robots on the factory floors, which were never thought about earlier. Robotics are also becoming soft robots, which will bring better human-machine interface. Robotics are going towards also now in the space, right? So rovers, ISRO's moon rovers, and so on. Underwater vehicles, that's going. So robotics and automation is spreading across beyond standard manufacturing industry. This is what this slide is talking about. And here in the last slide, this is my last slide. I'm just talking about what are the different research topics where today's researchers and academia can focus on many of these topics. Many of you might also already be working on. So some of these are modeling for control, robots modeling, which can be not only stationary robots, but also mobile robot modeling, environment modeling around the robots in case of mobile robots. Mobile robots can be ground robots, or it can be aerial robots, or water or seawater or underwater vehicles. Kinematics, inverse kinematics, and dynamics modeling of these systems. Lots of work already happening. AI and estimation techniques for the model parameter estimation, identification, tuning, and adaptation. These are the we also call it the digital twin of the systems and robots, right? AI and automation for automation robotics and subsystems used for the different industrial assets. So power plant chimney stack monitoring, wind turbine monitoring intermittently to monitor the conditions of the wind blade or wind turbine conditions and so on. Similarly, power plant conditions, equipment conditions through drone-based inspections or robots-based inspection and so on. Asset performance management for equipments in the factory floor or any different industry. The equipment conditions can be monitored through the sensing data or through visual cameras and so on. Right, so that's areas of research and applications and innovation. Robots use lots of work is also happening into different multimedia sensing estimation for the robotic application, right? For autonomous robotics, multimedia signals vision, combining sensing fusion, signal and image processing fusion, using visual lidar, microwave, IR imaging, and so on for robot navigation, guidance, and control. AI for cybersecurity by design. So cybersecurity today is based on, say, you look into mostly firewalls and so on. So to protect cyber attacks from outside. But what if cyber attacks are internal, which are not protected by the firewalls? So can we have digital ghosts of my system behavior? And can I have cybersecurity by design? So if I find there is some anomalytic operation, I can trigger, I can alert that something is wrong here. It's not, doesn't look like a normal operation. So that means somebody is trying to attack your system behavior through some mal-operation. So cybersecurity by design, which is also GE coined a term called digital ghosts. We work, a lot of work has happened in this area, which is still going on, and slowly it will penetrate into cybersecurity, which will be advanced cybersecurity of the system and will penetrate to industry subsequently. AI for robotic process automation. So many of the industrial, say, service management jobs, which are done manually today. Okay. So if there are 100 different, say, GE has 50,000 wind turbines. So how wind turbines service engineers have to be allocated the task based on the service condition requirement, right, by the service team. So manager has to allocate, okay, you go to this wind farm. These turbines are having some service requirement or maintenance requirement, repair requirements. Now those management has to be done, are done manually, as I told earlier. Now people are thinking about how can we automate those, and that's where Gen AI, generative AI, large language model, visual language model, VLMs, these are being used, or they are being actually explored. So Gen AI applications are penetrating into this kind of which we call it a robotic process automation. Documentation in the industry, right? How do you see cybersecurity documentation? How do you see documentation of different maintenance documents for different old, new, and advanced equipments and so on? So how do you manage those? How the common repairs, the common maintenance faults can be collated together, and can be AI, Gen AI based solutions to give you advisory to the human service engineers. And that's where, and these are the different, these and many more are kind of applications. I'll just quickly play this video to showcase. This is a long video. I'll just play a few points here. This is from the Mahindra factory. This video is available on the YouTube. Yeah, I have already put up the link. Now see, this is where your just a clip. Right? So this is where the automation is happening.
Either generated on site or purchased through green contracts. The human team, fewer than 30 people per shift.
Human robot operation together, right?
They manage the AI that builds them. Each wears smart visors that project repair
So
manuals that moments
now automotive plants of today and tomorrow are going to be highly automated with minimal human. Of course, human jobs are replaced, but from the day-to-day routine job are changing, and more robotic people are required now, robotic engineers who can program these robots, develop this innovation, robotic application. And automotive is one application area, but this kind of machine manufacturing plants will have many such robots applications coming into future.
long but barely a centimeter thick. They arrive in climate-sealed cassettes that link seamlessly
Hmm?
with Mahindra. Seamlessly with Mahindra's patented pallet system.
And this is one of the new plant of Mahindra which has come in Pune, right? So if you find time, you can also try to plan some visit for yourself or students, right? Part of this faculty development program or subsequently. Okay,
Yes, sir.
so I'll just stop this video, and we are done from my side, and we are. I can close this. Okay. Now we can have.
Hello, sir. Actually, due to time limitations and another resource person is waiting in the lobby, so we need to skip the question answer session. So if
Okay.
we need, if somebody needs, we can talk you through mail or through any kind of
Sure.
communication.
Yeah. So
so
what
it's,
I will
time.
request is you can collect the questions. Okay.
Yeah. Yes, sir.
From whatever questions are there, you can collect and send it to me, and I'll try
Yeah.
to address those. Yeah, and
Yeah,
send it
sure,
back.
sir. Sure. So now it's time for vote of thanks. On behalf of organizing committee of this ATAL FDP, I extend my heartfelt gratitude to our distinguished resource person, Dr. Jayesh Barve, sir, Principal Control and Optimization at GE Global Research Center, Bangalore. Sir, your insightful session, rich with your vast experience from both academia and industry, has truly enlightened us. The way you connected theoretical aspects with the real world industrial application has been very inspiring to all the participants. Your contribution in the form of patents, research, publication, and industrial products are a true reflection of innovation and excellence. We are extremely thankful to you for taking the time out of your busy schedule to share your knowledge with us. I'm sure the participants have gained valuable perspective that will motivate them to pursue impactful research and innovative practices. Once again, thank you very much, sir, for your valuable contribution to our FDP. Thank you. Thank you, one and all.
Thank you, Jay sir.
Thank you. Thank you so much, and I hope this would be useful. And look forward to
Yeah,
any
yeah.
questions and come back to that.
Yes, sir. Yes,
Thank
Yes,
you.
sir.
Have
We
a
will
good time.
communicate
Thank
with
you
you.
very much, sir.
For the remaining part of the FDP. Thank you.
Thank you, sir. Thank you. Dr. Chetan, sir.
Yes.
Mr. Mahesh Mohan Patel sir is there.
Yes,
So
yes.
we'll start the process of welcome.
Yeah. So we welcome our second resource person. It's my privilege to introduce our esteemed resource person, Mr. Mohan Patel, who holds both BE and ME degree in instrumentation engineering. He brings with him rich expertise in industrial automation, PLC, HMI, and SCADA system, with extensive experience in handling live projects, industrial projects. Mr. Patel has successfully completed several impactful industrial automation projects, including upgradation of Siemens PLC and HMI system to S7 1500 PLC and unified HMI for paper reminder at JK Paper Limited, Surat, and the upgradation of Siemens S7 200 smart system for the oxygen plant at Paper Rudrapur, Uttarakhand. He has also worked on ABB drive repair and operation updates for the Slitter machine at Modern Metallic Surat, and currently engaged in the upgradation of Wonderware in Touch SCADA to Siemens WinCC SCADA system for reheating furnace at L&T Forge, Surat. In addition to his industrial contribution, Mr. Mohan Patel has been appointed as a professor of practice at Sanjeevani College of Engineering, Kopargaon, Maharashtra, where he shares his rich industry experience with the budding engineers. With his strong academic foundation, hands-on industrial experience, and commitment to bridging the gap between industry and academia, Mr. Patel continues to make significant contribution to the field of automation and instrumentation engineering. We're delighted to welcome him today as a resource person for our ATAL FDP. Thank you, sir. You can start. Hand over to you.
Good evening, everybody. Hope after a session of 2 hours, people may need little bit break. As a student, we get little bit tired. We are habituated to learn only for 1 hour as a being a student. But being a practitioner or being an academics, we should increase our little bit capacity. I'll be happy to share my experience with you people. I love to teach the students. I have completed many projects in industry. Currently, I am in Solapur for completing one project for tin bending machine where I am working with Flexen PLC. I have done many projects in many domain of industry like food industry, steel industry, paper industry, chemical industry. So I have completed many projects in industry, but I love to share my skill with people or mainly students. I have major portion of my experience is shared with the students. So I have academic experience since 1988. I'm sharing whatever I am having little bit. I can enjoy the session with the students of engineering, polytechnic, ITI and all. And my effort will be to reduce the gap between academic and industry. What happened is being an academician, what we feel is my students are better, they should get better job. And being an industry person, what I need is I should have a better engineer who is having a very much strong background of engineering. Today, what we are lacking there is a gap between academic and industry. What is the gap? There is nothing gap, but see the presentation of whatever we are teaching in the college, how it is connected with industry. That is what we need to focus on, and we need to deliver it to students. Before me, sir has guide you regarding latest technology, latest upgradation. Today, there are latest trends of IoT, industrial IoT, robotics and process automation, AI, ML. Everything is going very fine, very fine, very fine. But how that technology, how that concept is being transferred to the mind of student, and how that all concepts we can make available to industry. See, there are good concepts are there, good ideas are there, good skills are there, good thoughts are there. But on ground, how much we are able to make it successful. So whatever the lacking is the basic fundamental of engineering. We are, as an academician, what I should say, we are lacking to make those fundamentals of engineering strong in the mind of student. Industry badly need engineers, and engineer students are facing a problem of getting job in industry. Why? Because they are not having their background fundamentals clear, so that whatever they have learned in the college, they are not able to visualize what my skill is, what I have learned, and how I can relate with the industry. So my little effort will be, I will not try to give you highlight of what current industries or what current trends are there. That's already shared by our uh, experts, and they are most talented. My little effort will be how we can relate the academic with industry in simple language. So my effort will be, we will take little few one or two or three examples how we can have Industry 4.0 or industrial IoT or IoT based automation. Automation, we know that automation is applicable in all field of engineering or all field of life, we can say. Mechanical, electrical, chemical, process industry, aeronautical industry, aviation industry, petroleum industries, communication is everywhere. Automation is there. Or not and everywhere, every field of life we touch the automation. So exactly what automation is and how we can practice the automation in day-to-day life. That is what we will try to see, and how we can use IoT in that automation, industrial IoT or the automation with IoT, because today's era are IoT era. And what is the major lacking, that in engineering colleges, all the students are having mobile in their hand. They cannot leave the mobile. They cannot live without mobile. So what our duty as an academician, that whatever they are having in the mobile is a tools today to operate the industry. So we should make students comfortable with our education and how we can use their mobile to operate any industry. So if we can give little hint to them, this way you can lead the industry. We as a professor, I cannot steal the mobile from the hand of the students, but what I can do is whatever the mobile he is using to chat or to have the other activities, if I try to mold his mind that whatever you are learning, you practice with mobile, so that tomorrow you have to use mobile as a tools. Mobile should not use you as a tools. So today's effort will be a little bit, I will try to demonstrate how we can have industrial IoT, that is internet based automation, how we can do that. We'll try to practice little bit. And for that, I am using one software. There are many companies working on industrial IoT or robotics and process automation. Many, just like Siemens, Siemens company is a good company. They are implementing IoT or AI machine learning. They have developed the libraries for AI and ML, and IoT libraries. They have developed the IIoT libraries and S7 1500 PLC. In that, they have developed this library. We can call that library. We can use the different instructions of AI and ML in that library. We can develop the code and we can integrate AI with Siemens automation. Similarly, Codesys is one company from Germany. They are also little bit there in industrial IoT. So if I'll try to give you some examples. Before going to that, let me share my screen. That I'll show you some screen on different application of automation, in which different field we can apply automation. So there are many field or many applications in your screen. Sir, is my screen visible to you?
Yes, sir.
Okay. So right from academic to industry, we can have various application of automation. Like in academic, if we bifurcate or if we go for the different education streams, that is different. If we go for different streams, there are mechanical, electrical, electronics, computer, chemical, all different streams are there. And if we see electrical or electronics or computer, whatever we are studying in academic, For automation, we generally require digital electronics or digital logics and or logical operations. Whatever we have studied in academic, we will apply in industry. So I have covered some little examples of what are the different logic gates, how we can operate the logic gates, what are the different applications where we can apply automations. So let me show you different examples of automation. Just like if I take simple example of lift. So if in home automation or in various uh, home automation, if I give the example of lift automation, if in my building there are lift of 5-story building, and if my lift is at 4th floor, and if I click on the ground floor, my lift is coming down, and whenever it reaches the ground floor, it should stop. So this is the one of the example of automation that in building automation or home automation, we can use automation in everyday life. So automation in society or home automation. So this is very little example of home automation. Now how I can operate through internet. So if you permit, I will try to share one link. So whatever the participants, few of them, they can click on the link and they can operate from their mobile or their laptop. If you are having the laptop, I can share this link in a group. Let me share this link in a group. Uh, I have shared this link in a group. Anyone, sir, you can. Now, what problem over here is light has gone. So I don't know whether I am or not.
Okay.
So there is no light in my room. So just I am in dark. If you have
Okay.
this link, just click on the link. Can you
Yes.
click on the link, sir?
Yes, sir. Yes, sir.
Click on the link and say visit site. Are you able to get something?
Uh, Sir, actually, it says something redirect notice.
Huh?
Okay, I will again click it, sir.
Click on
No,
the
no,
link.
sir. That link is not, sir, useful, sir.
Okay. Let me share one more time.
Okay.
Uh, I have shared this link on next gen group.
Okay. Okay.
Please click on that link.
I will send that link to our participant group.
But I request participants that do not operate. Everybody don't try to operate at least one or two, because see, if all will operate now. So there will be one lift, 50 people will be operating. So it will get confused what to do, what not to do. So you just operate it first, then share it to others.
Yeah. Yes, sir. We can. It is visible now.
Visible. So are you able to see the lift?
Yes. Yes.
Okay, now click on the C4.
Okay. C4.
C4. Yes.
Yes.
Now you are operating
Yeah.
from your mobile.
Yes.
Now click on the button C1. So my lift is on 4th floor. And if you are calling on first floor, see, program is
Yes.
there in
Yes.
my laptop. This is not
That lift is
simulation. This is
coming.
actual program running in the PLC. So if I show you, this is my visualization which we have developed. This is called partly is called SCADA software. And if I want to, I can show you the PLC program. Let me switch my screen so we can better visualize it. So this is the different software. If I tell you that, okay, click on the home. Okay, you are getting different screens, right?
Yes.
Okay, now click on the bottle.
Yes. Again,
Now
different
you
screen.
are able to operate that bottle filling plant. So one of the application of industrial automation is you are operating that bottle filling plant from your mobile. Select red, blue, and green. Either any one of these are the three products we need to fill into the bottle. So select any one of the switch red, green, or blue.
Yes. It is not taking input, sir.
Okay, let me just see. I am giving the command from here. I am starting the
Okay.
system. I am starting the system and I'll say go. Okay, now somebody else is operating this. So we are giving say
Yes.
home automation tank level control systems.
Yes. Yes. Yes.
So if you start that switch, no tank will get automatically filled. I have started the system. So my tank is getting filled. I'm getting the actual level of the tank side by, and my pump, whenever my pump is on, my water tank will be filled. When it is full, my pump will be off. And if I'm getting the water, level of the water in my tank will be reducing. So real time pictures I am getting of the plant, and I'm able to operate the system from remote location. This is what
Yes.
industry IoT is there. So I'm applying automation with IoT. So there are many applications. Now, if you click on the home, just click on. So this is one of the application where we can apply automation. Automation not just with PLC. This is a real software from Codesys company, and I am using my laptop as a PLC. And one more thing is, see on the bottom side there, click on home button, sir. Are you able to click
Yes,
on
sir.
the?
I'm trying, sir.
Yes.
There may be a network issue at my side. Yeah. 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 Yeah.
Okay. Now click on
Yes.
the robot cylinder. This is smart society operation of one motor from multiple house. So if in our society there are centralized motor is there, from one building I can be able to start and stop the motor. So from building number one, my motor is currently on. So from second button, that is red button, if you press and red button from any building, you will be able to stop the motors.
Yes. Yes,
So
sir.
this is what
It's happening.
industrial IoT is there. So this is not just a simulation. My laptop is being getting used for programming. So if I can show you the program, this is my graphical user interface. And if I show you the AND gate operation, being an academician, professor of engineering, electronics and telecommunication or electrical or computer, we are teaching AND gate operation to all. So if I show you, this is my picture, and if I can show you the PLC program, I'll start the PLC program side by side. So this is the PLC program of logic of AND gate operation. So this is my logic of AND gate operation, and this is my graphical user interface. So if you operate to see what is the AND gate. AND gate means whenever both input are high, then and then my output will be high.
Yes, sir. I'm operating from here, and it
And you can
shows
see
for
the
one
radar
one.
diagram also. The program also you are getting visualized. Now you have opened the robotic arm. The robotic arm means in industry, yeah, yes, keep it, leave it open, sir.
Okay.
Robot with cylinders. Now it is your program open is material handling system. Leave it open. Material handling system means in any material distribution system. In the bottom side, I have 5 receiver are there. My feeder is stopped at receiver number 1. And if I click say tank number 4 is empty, and if level at that tank is low, then my feeder will go to that particular tank. Whenever it reaches, it will start control valve and feed the material to that particular feeder. So this application specially used in textile industry, that is cotton ginning and pressing industry. So wherever ginning means we are हम सरकी निकालते हैं कपास में से. So there are 10 machines will be there who are taking out the cotton seeds from all cottons, and whichever machine is empty, he will call the feeder that I am empty, so please feed me with the material. So my now second tank L2, if it get empty, my feeder will go to that particular tank, and that material will be feeded to that tank. And as soon as it is feeded, level is on, my valve will be off. So this is IoT and industrial automation. So this, whatever I am showing you, this is the general practice in industry, that they are doing the programming, they are operating the machine with some SCADA software, with some GUI. I am adding one more step ahead, that is addition of internet with automation, that is industrial IoT. So I should be able to operate my plant from remote location. So this is what today we should teach to the students. So we are teaching the students IoT, and industry are now, they are all industries, conventional automation, now they are moving towards the industrial IoT, because IoT is the today's IoT is today's demand. And these are the various application of automation. If we apply little bit IoT to that automation, we can better understand or better regulate the plant. So this my little bit effort to share you. See, my feeder is moving continuously left and right because two tanks are empty. So I will make L2. So whosoever sensor is on, feeder will go there and then again come back to the next one. This is what is happening. Click on another application, sir. I am clicking on the warehouse automation. Warehouse automation means I am having the, just like big bazaar or DMart or big stores, we are bringing the material from outside. We want to place it at the particular place. So whatever the material I brought, so I want to place that material in C44 compartment. That my motor, down motor will be on and my left motor will be on, and till I reach there. So this is the automation application. It is a fun. Fun come means we can operate the plant from remote location. This is what experience I want to give to you people. So if you really implement this idea in industry badly need, because they are facing the problem of labor plus skilled labor. So we are the academicians, we can better provide solution to all industries. So if we put our little effort in automation, we can give the industrial IoT. Traffic light automation and street light control. We need the street light control. That is, if I can give you one more thing, multi-speed motor control. Multi-speed motor control matlab, मेरी कोई motor है, I want to operate that motor with multi-speed, and I need specific pattern of operation of the motors. My motor is currently off. If I want, I can start the motor at slow speed. My motor is currently in off position, so it is not running. If I click the button, low button, my motor will start in a low speed. And if somebody press medium button, motor will start running. Sir, press the medium button. Somebody please press medium button.
I would like to ask participants, because I already took the experience.
Yes.
Any of the participant, please press the medium button through that link.
Sir, have you shared the link?
Yes, I shared the link.
So tell them that visit site. They have, whenever they click on the link, they have to accept the visit site, and after certain, yes, good. Now we are operating the motor at medium speed. Now press the low speed.
Yeah.
If you press the low button, motor will not go back to low speed. This is my logic. My condition is, if my motor is stopped, it should start in first gear only. And from first gear, it should go in second gear only. And from second gear, it should go in third gear only. It should not go back to second gear or first gear. So after high speed, it should get only stop. So this is it was my logic that I should be able to operate the motor in any one direction only. So there are some situations where we should be able to, okay, let me stop motor first. There are some situations where we should be able to operate in specific pattern only. We can start just like our motorcycle. We should be able to start the in first gear only. If I press the low medium button very first, it should not accept my second gear button, second gear command. It should not gear accept the third gear command also. My motorbike should start only in low gear command. And from low, if I want to jump to high, it should not accept. If I stop the motor, it should not get stopped. It should go in medium speed only. So this was my logic. So this logic, how we can develop? In order to develop that logic, we are using control system subject, digital logic subject, and through control system subject, we are developing the logic equations, and that logic equation we have applied. Now, this is the visualization you are seeing at your end. If I can show you the logic diagram or PLC program for this, let me click on the PLC program also. So you will be enjoying little bit.
Yes, I'm operating that
You
motorcycle.
are operating the parallelly. Let me show you the program of PLC.
Yes, yes,
How
sir.
that program is getting operated. So people will they will enjoy a little bit.
Yeah.
So this is what we can do. We can add. This is the real-time operation of what I can say. This is purely engineering and purely whatever we are teaching in the classroom. My A and B, 1 0. If 1 0 is there, there is a 2 number. So 2 number means second speed. I am getting the second speed. If I am clicking on the height, okay, let me get this also. Yes. Now somebody has stopped. So when A and B both are 0, my motor will be 0. If I press 1 low, then 0 1. 0 1 is 1 number. So if I press low button, 0 1 will be there, and 0 1 means A and B. That is digital numbers, binary numbers we are teaching to the students. And if it is a 0 1 number, because in digital there is no 2 3 4 5, only 0 or 1 is there. So in digital circuits only 1 0 1 0 is 1 0 1 0. The whole computer is working on 1 0 1 0 1 0 1 0. But in order to get multiple numbers, we are converting all that digital number into binary, and we are taking care of individual specific bit, when to get on, when to get off, and by combining different bit, 2 bit, 4 bit, 8 bit, 16 bit, 32 bit, 64 bit. Today's whenever we are going to purchase computer or mobile, we are asking how many bit processor is there. So it is a 64-bit processor or 32-bit processor or 16-bit processor. 16-bit means what? So 2 raised to 16. So we are dividing total journey of numbers into 16-bit, 2 raised to 16. That is 32767. And 32767 number, if I want to play with that 32,767 number, I can convert 60. I have to take 16 different bit, and I will be having a combination of all that different bit to play with all that numbers. So this we are teaching in the academic. But if we show them application of whatever we are teaching in real time, or industry need this, so we can better relate our academic or our delivery to students. Now we can switch to one more application. Sir, click on the home button. Any participants, please click on the home button. You can have escalators. We are teaching XOR gate. Let me show you first. Click on the XOR gate first. Exclusive OR gate. Exclusive OR gate means we are teaching in the classroom exclusive OR gate. But where it is applicable, whatever we are teaching to the students in college or in classroom, it is going to be useful in real life. Real life means outside the classroom. Outside the classroom, maybe our home, our street, our village, our state, our country, and whole world. So I am teaching exclusive OR gate to student. Wherever A, B bar or A bar B, means either of one switch is off, my output will be on. So where we are using that exclusive OR gate in our home, like staircase wiring. So I am going up from down. I've started the light. I'll go up and stop the button. Again, second person came into our home. He will start the light from bottom. It will go upstairs, on from there he can stop the light. Or any person coming from the top, he can start the light and When it reaches to ground floor, he can stop. So this is the application of whatever we are teaching in academic. Similar example, if I can say, same example, this is the application of exclusive OR gate of electronic engineering, electronics and communication, electronics engineering, electronics and computer engineering, industrial electronics, electrical, all branches, they are teaching this subject. But where to use it? Our duty will be how, where to use our knowledge in outside the classroom. So our home will be the one of the example. And similar example, all railway station, we see escalators. Escalator means if people came to the sensor, bottom sensor, escalator will start automatically. When it reaches to the top, escalator should stop. If person coming from the top, if sensor senses, escalator should start in downward direction. Whenever it go out, it should stop. So we should show them applications so student will be more focused and they will be able to visualize their fundamentals. So whatever we are teaching in the classroom is basic fundamentals of life. And we should show them there. Here you will be able to use. Here you will be able to use. Here you, so if we show them the different example, they will be better understand the application of our delivery. If I can click on the street light. Street light means we know that in our day-to-day life, all roads are in night time. Full light will be on all the time. If I want to save the energy, if I want to optimize the consumption of energy, if I start the car, anybody who is seeing this screen, street, automatic street light, any faculty?
Yes, sir.
This. Click on the switch,
can-
turn on the switch. So you will be able to visualize the how street light, automatic operation of street light works.
Okay, sir.
Any faculty, please.
Yes, sir. Trying, sir. Anyone from participant can do that.
Automatic street light control. Sir, yes, good. See, my car is moving ahead, and whenever it reaches to one sensor, previous light will be off and next light will be on. So this is the application of street light control. For that, we have written the logic. So our little application of our delivery, if you can show that this is the application where you can apply your knowledge. For that, what I have written, I have only concentrated on one light. One sensor is able to start that light. Another sensor is able to stop that. Just only start, stop, start, stop, start, stop, start, stop. So this is, and if similar application, this is the, means there are only two sensors are responsible to start or stop any one light. And same I'm repeating for another one. Just operate only one. My sensor reaches to sensor 1, so my light number 2 is on. Now if it reaches to 3, my light number 2 will be off. Please don't operate switch many times. Leave the car, reach to destination. And when my car reaches to 4th sensor, my 4th light will be starting, 5th light will be, when it reaches to 5th sensor, my 4th light will be off, 5th light will be on. And if you connect this with hardware, if I can show you, this is not just simulation. If I can show you my IoT device, that is Arduino, I have connected Arduino with my laptop. And if I can show you, there are in, so these are the applications of connection of IoT with automation. Now, how I can connect different IoT devices with my laptop? So there is a project in this Codesis company. They have developed the software so that our laptop can be used as a PLC or programmable logic controller. And with that, what I have done is I have connected my Arduino Uno through Modbus client and slave communication. So I have connected my Arduino with laptop, and there are green rounds are there. Means actually my Arduino is in running condition. If I connect my hardware with Arduino, and if I connect this hardware, that is relay and lights and motors, I will be really will be able to operate hardware from your from your premises. So this is the real application of IoT with automation. So my effort was just to share the latest technology with basic, very fundamentals. One more thing I will let me share. Who can do this programming? Generally, while coding or while asking the language, see which language it is, which language, who can do the PLC programming, or who can do all this engineering. So there are many branches are there. Mechanical is there, electrical is there, electronics there, microprocessor is there, computer are there. So who can do this programming? So all engineering engineers or all engineering graduates can do different programming in their comfort zone. If I can show you simple examples of different PLC programming languages. Mechanical people, what they feel that PLC is not our subject. PLC is the subject of electronics only. Electronics people say PLC is only my subject. Electrical people should not enter in my domain. Microprocessor people, they say that we are the king of the coding. Nobody can beat us. Computer people, they feel that C language is our heart. Nobody should touch it. It is not the case. In PLC, many domain engineers, many domain streams students. How we can do different PLC programming languages. If I want to do the coding, let me show you. This is the software developed by Codesis company. If I can show you about this is the Codesis company who has developed this software. Now, if I can show you the different other companies, if we go with the ABB companies, ABB means if I can show you how we can write the code in different PLC programming languages. So if I'm an electrical engineer, I know better understand the pattern of wirings. I have developed the program for different PLC programming language. If I am electrical engineer, I am very much comfortable with wiring pattern. So I have simple developed the program to start the motor. If I press the start button, my motor should start. If I press the stop button, my motor should get stopped. This is a simple application that we can run for PLC. So this is my PLC program, like what we have done in this Codesis. In Codesis, you have seen that ladder diagram language is there in which we can do the codings. If I can show you the same program, let me show you simple AND gate and OR gate. These are the switches in series or parallel. So this is the pattern of programming PLC. Similarly, if I am from electrical engineering, I better understand the language of series parallel. If I can give you the GUI, graphical user interface. This is my graphical user interface for, this is my PLC program and this is the GUI I have developed for ABB company PLC. Whatever now I'm showing it software from ABB company. And that software is also based on the Codesis software. So if I'm operating this, if I press the start button, my motor will start. Okay, let me start it online and run the PLC. If I press the start button, my motor is started. Even though I release it, my motor will remain on. If I press stop button, my motor will get stopped. So this is the this is the program which we have written in the form of ladder diagram, so which electrical people can better understand this language. Now, electronics people, they say, no, we are not comfortable with this. We are very much comfortable with AND gate, OR gate language. So if I want to write the same code in AND gate, OR gate language, it is called function block diagram. Function block diagram means parallel means OR, series means and not means inverted. So they better understand the AND gate, OR gate language. So same code we can write in another pattern that is called function block diagram language. And if I can show you how it is getting operated in function block diagram. So this is my start and stop button. If I press the start button, my motor will be on. If I press stop button, my motor is off. Function remains same. This is white color. I could not convert into I could not change the color. So in while writing the program, it's while exciting that color is same and same. That's why it is not changing its color. So start button, motor is on. If I press stop button, motor is off. So you are able to see this, how electronics people also can write PLC programs. Similarly, if you are comfortable with microprocessor and microcontroller, in that how we can write the coding. If I go for IL, instruction list, this is the instruction list language. Instruction is assembly language programming. That if I want to write the coding to start and stop the motors, how I can write code, that is load start one or motor one and not stop then store motor. So this is the code to write programs for starter in microprocessor or microcontroller language, that is called assembly language program. If I can show you the graphical presentation of IL visualization. This is my how I can develop the graphical user interface GUI. So I'm operating start one from my button. So from remotely, I am pressing the start one. My motor is on. Even though it is released, it is off. If I press stop one, my motor is off. So this is also one of the way to write a PLC code in PLC programming. If computer people are there, so we are the master of coders. They also can write the program in their domain. If I write the program in C language, it is called structured text language. C language is this. If I write an equation, that is motor assigns to start or motor and not stop. So this is the code of writing a program in PLC. If I try to operate it here, same result is there. If I press start button, my motor will be on. Even though I release it, my motor is off. If I press stop button, my motor will be off. So this is the live example of, and one more, another language, if I can show you, sequential function chart or sequential flow chart. Anybody who is expert in flow chart, he also can write the program in flow chart language. In flow chart, we know that initialize the data, collect the data, and if we have the transition from start for button, we jump to second step and we assign the output. We wait for another step. So if I try to operate the same program through sequential function chart or sequential flow chart, same operation will be done. I'm pressing the start one button. So if I start button, my motor is getting on. I jump to step number 2. My motor is on. Even though I release it, my motor will remain on. I have set the motor on and I'm waiting for stop button to press. If I press the stop button, I'll go to step 3 and reset the motor. And whenever I press the stop button, my motor is got off. And as soon as I release that not stop, I'll go to initial level. So this is another language to write a code. So in order to give easiness to operator or developer, companies have approved 5 different PLC programming languages. First is ladder diagram language that electrical people better can understand. Function block diagram language, that is AND gate and OR gate, that electronics people can better understand. Computer people can better understand. So there is a language that is structured text language. Instruction list, that is microprocessor, microcontroller language is there. And somebody who is proficient in flowchart, he also can develop the program. So this is not the proprietary. This is not proprietary, but all engineers can program the PLC in their own way. And all the languages having some plus, some minus. And all countries, they are preferring the language based on their comfort zone. If you go to America, USA, they are preferring ladder diagram language. If you go to Europe side, they are preferring instruction list language. If you go to India, in India, we are preferring ladder diagram language as well, function block diagram. And somebody who is if you want to write the script, then we can write the script in structured text language, just like C language. All languages having certain plus and certain minus. Ladder diagram language is very easy to understand, easy to trace out. If we are stuck in some program where we are stuck, we can easily visualize the status of our program and we can easily trace out the problem and solve the problem. Whereas the limitation of ladder diagram language, if I am having the ladder of 1000 rungs, then execution time will be more. That is the limitation of ladder diagram language. Function block diagram language, FBD language, execution time will be less little bit, but very difficult to trace out the problem if there is nothing, if something is not working. Structure text language, that is C language. It is good for skilled person. All may not be comfortable with C language. So based on your comfort zone, you can develop the program in any language. So these all 5 different PLC programming languages are being approved by IEC 61131. That is International Electro Commission, who is the agency who is approving all these different PLC programming languages. They have approved these 5 different PLC programming languages in order to give comfort to end user, that is a developer. So we are the end user of development. All these GUI, see, ladder diagram language, function block diagram language, sequential function, these are the graphical based language, and structure text language or instruction list language is very basic language. At the very beginning, whenever the PLC got invented, the whole code was being written in assembly language, or second we can say instruction list language. So these are the text based language, and the function block diagram, ladder diagram, and sequential function chart, these are the graphical based language. When we compile the program, finally it is getting converted into hexadecimal code, and that hex code only go to the microcontroller IC. Now one more thing people will ask, that what is the difference between IoT device and PLC? So PLC is nothing but inside there is a microcontroller or a microprocessor is there, but that microcontroller or microprocessor is being developed, or it is being connected with different protected device, that isolators are there. All the components are designed so that this PLC can be used 24/7, 365 a day in rugged environment. It can be useful. That is why PLC is there, but inside there is a microcontroller. It is just man with only head and man with protected head. That is the difference between, there is only difference between IoT devices and PLC. IoT device is the bare brain without protection. If we put all protection, it become a PLC. So this is what the difference. So today's IoT devices are working on 3.3 volt or 5 volt. So it is very voltage sensitive. Low power devices are there. So we have to be very careful while handling the signal. If my signal is of 1.2 volt and if my noise is of 1 volt, then I'll be getting only noise instead of signals. So if we are able to filter the noise, if we are able to optimize the impedance, then we can say we can better control the industry with IoT devices. That is what only the things. So my effort was only to just to give you that whatever there is in automation, we by allowing IoT little bit, we can be able to operate the any plant from our home. So remote monitoring and control of industry. That is what industrial IoT. And this is the today's requirement. Previously, it was like controller was at different place, sensor were at different place, and final control device was at different place. Now we are clubbing all together and we are able to operating the different from whole plant from different location. This is what industrial IoT is there. So this is what just I was about to share with you, and sorry for delay. So I could not come in time because I was engaged somewhere, and I actually, if I apologize for this, I forgot the date and time. So I was in a road. So I just came to my destination and I am trying to share with whatever I am having it. So this is what I am there to share with you. If you are having any question, you are welcome, sir.
Yes. So I would like to ask the participant, please ask the questions if you have any. One question at the time of your presentation, sir, there is one question I remember. How the system is secure, because from such a long distance we can able to operate it. So is there any concern about security?
Yes, sir. There are many concerns about security, not only security. See, whenever we put our brain in air, we have to take care of many things. First, not only security, but connectivity also major issue is there. Whenever I'm putting my controller on the internet, somebody may steal it, somebody may hack it. So I have to take care of what are the parameters that can be hacked. So I have to secure my system. That is one issue that we need to solve it. One more thing, connectivity. If I'm losing the connectivity, I will not be able to get my plant at my tip. So we have to work with many. See, this is one area where we can improve ourselves. Parallelly, we have to take care about the security plus connectivity plus frequency of operation, time stamping. These are the many parameters we need to take care. So if we take care this much, then definitely we should go for industrial IoT. And this is the demand of time, today's demand. Nobody is trying to do hard work. What we are, our limitation is being a human being. Now we are habituated, we are lazy little bit. We want many things to do at same time. We don't have
Yes.
patience to wait for things to do. So I want to at my home, I want to chat this also, I want to do this also, I want to do this. Similarly, industry also not wait to finish one task, or they don't want to get depend on the person. Just like AI, what we are doing AI. So whatever the person is doing, they are actually industry is putting their hand in AI, who is not existing. So industry is putting themselves at a risk. But considering that AI may not misuse it, so we have to take care about the algorithm development or whatever the data we are feeding. Similarly, whenever we go for IoT, we have to take care about the bandwidth of operation, frequency of operation, security that we have to take care, that IT people can better understand. One more thing, these are the base, electrical, mechanical, civil, these are the base of industry or base of engineering. We can get the data real time scenario from these three branches. Computer and IT people will take care of data handling, data analysis, data fetching, data analysis, all that they can. So everybody will be getting involved. Previously only mechanical we were doing. There was a little connectivity. There is very little connectivity was there between different streams. Now all stream has to come together and they have to take care of about their responsibility. Previously we were not bothering about data because with hardware only we were running our plant. Now I want to increase my capacity, I want to increase my quality, I want to increase my consistency, and I have to upgrade my plant as per the current trend and current tools. So IT is the current trend, current tools. So we can involve IT in our applications. So IT people, if we get the data, they can better fetch it, they can better analyze it, better monitor it, and better present the data. That is what it is being happening. So IT people they are coming, computer people they are coming, electronics people they are getting updating their application of whatever their ideas.
Yeah. So anyone from the participant have any questions? Okay. So, Dr. Patil, ma'am, are you there? Okay, sir. Okay, so before proceeding to the official vote of thanks, I just want to mention you that, sir, first time I have received such a wonderful experience that in online mode I have got hands-on experience, which is the first time I have experienced, and I think most of the participants also. Uh, so thank you for that. So let's move to official vote of thanks to Mohan Patel, sir. On behalf of organizing team of this ATAL FDP, I sincerely thank our esteemed resource person, Mr. Mohan Patel, Professor of Practice at Sanjeevani College of Engineering, Kopargaon. Sir, your session has been highly enriching, giving us practical insights into industrial automation, then PLC, HMI, and SCADA system. The way you shared your experience from live projects, including upgradation of Siemens PLC, HMI system, SCADA solutions, and drive automation, has provided participants with a real understanding of how industry challenges are addressed with effective engineering solutions. Your contribution has not only enhanced our technical knowledge, but has also inspired us to bridge the gap between industry and academia through the applied learning. We are truly grateful to you for accepting our invitation and for sharing your valuable expertise with the participants. Thank you once again, sir, for your time, efforts, and insightful contribution to this FDP. Thank you, sir.
Thank you everybody and have a good night and better tomorrow.
Yes, sir.
because we are the responsible for leading our youth to a new height. We want to lead our country to a number one in world. So we are
Yes.
the responsible sources for this responsibility. Thanks
Yeah.
everybody and have a good
Thank
night.
you very much, sir. Good night. Thank you. And all the participants, we will share you the feedback link soon. Please be in touch. Thank you. Thank you, one and all.
Thank you. Thank you. Thank you, sir.